Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Yes. Good evening. I welcome you all for the day 3 of Faculty Development Program titled Innovations in Additive Manufacturing for Green and Sustainable Future. Now, the session 5, Swarm Intelligence for Minimizing Waste in Additive Manufacturing, will be delivered by Dr. A. Tamilarsan, sir. It is my immense pleasure to welcome Dr. A. Tamilarsan, sir. Welcome you, sir.
Very good evening, sir.
Dr. A. Tamilarsan, sir, received BE Mechanical, M.Tech Machine Design, PhD Mechanical from Anna University. He has more than 15 years of teaching and 8 years of research experience. During his teaching and research career, he got many awards such as Best Faculty and Outstanding Contributor to Elsevier publications. He has published more than 40 peer-reviewed journals, including 12 Q1 articles. He has established Center for Advanced Manufacturing and Material Processing Research Centers. His research expertise are optimization techniques, composites, and he is very strong in artificial intelligence and machine learning techniques also. Currently, he is working as associate professor in the Department of Predictive Engineering, Savida School of Engineering, Savida Institute of Medical and Technical Sciences. I welcome you, sir.
Thank you so much, sir.
Now, I kindly request Dr. Tamilarsan, sir, to start session 5.
Sir, thank you so much, sir, for your valuable introduction on me. So, very thank you so much. Shall we start, sir, now?
Yes, sir.
Okay, thank you, sir. Very good evening, all. Sir, is the screen is visible, sir? No?
Yes, sir.
Okay. Very good evening to all for attending today's the session. So thank you so much for DSCT, our organizers, Madam Radhika Madam, and for our Professor Rajesh Shekaran sir for organizing such a wonderful FDP that is relevant to our additive manufacturing process. So thank you so much. So I hope the past 2 days you learned on the main topics of additive manufacturing process. Start from the like rapid prototyping and from the different FDM, SLS, and inkjet printing. So many things we discussed. So I don't want to go for too much on the basics. That already I hope all our professors and some of them research scholars, some of them PG level students, some of the participants. So we don't go for too much of basic introduction. So we go for directly on relevant to the topic, more specific in this area. So our title on related to the swarm intelligence for minimizing waste in additive manufacturing process. So connecting to the title, today artificial intelligence playing more well all our core engineering subject. So in this sense, we try to use such intelligence methods to minimize the waste in the additive manufacturing process. All we know about it is these products called as the add that material by some kind of techniques, some methods like this. So we need to minimize some kind of burst through some kind like swarm intelligence techniques. So that we go on one by one. So in this part, see, there are two that is that is the main things. One on design as a service. Or once if we are fabricating our product, so maximum we to deliver. So there are two techniques: intelligent AIM and design service. We strictly using on this. Most of them interconnected. Design as a service DAS, and the second one manufacturing as a service. So here we have different categories like process selection, manufacturability, and the evaluation, and the design exploration and exploitation. We will see most the topic of exploration and exploitation behaviors while discussing in the algorithmic procedure. Then moving over there here, mass on this APP and PKAM, that is process knowledge management and virtual commissioning. So this can be adapted towards in the human machine intelligence in decision making. So there are 5 things they present here, role models like designer, next innovator, and engineer, manager, and customer. So here only we need to connect our MI, that is machine intelligence, or maybe an artificial intelligence. We are going to connect for this, because human machine intelligence more important for making the good decision. So in this slide, we noted down this information, and moreover here, the product service, finally we are delivering to the product to the particular customer, maybe on medical or maybe on some appliances, something like that. So as we know about all that, our 3D, that is additive manufacturing process, this is illustration on this. And from the CAD model, we are preparing the CAD model. Then from that, we are feeding to the machine. And here there are the different sensors which we utilize to monitor that process. So what happens during the process? So here we try to embed, there are two things. One on AI algorithm, that is deduction classification, any deviation changes like this. So just we back to our manufacturing technology, tool condition monitoring, TCM. Same like here, we are doing on deduction classification. So here we are embedding the printing process parameter optimization algorithm. That rose color, that red color represents here our area, how to minimize our that is waste in this zone. And here how to adapt the swarm intelligence algorithm to make more robust the process to perform in best way, so through the electronic interface. So this area refers here different methods we to adopt, biomimicry process we to adopt for performing the process to minimize the waste. How we minimize means by adopting the different types of swarm intelligence algorithm. The blue color line represents here. I hope you are familiar in this slide. So most of our work connected to, there are three components. One on all we know about, first of all cost, second one time, and the third one more flexible. That means more robust needed for making even in the small parts to some complex part. So over to that cost here, less material waste, our important part, because most of the time if you improper printing parameter, something we adopt means the system may produce in different components. So what happens here, again we reuse for the different purposes. So that what we do, our main target initial itself, we try to minimize our material waste to minimize. Okay, this is the one of the shake of one example. For your better understanding, improper printing parameters. See here, for fabricating one part, there are different the component not manufactured in accurable manner. But if you go for after adopting the different strategies like printing parameters based optimization, once you performed through swarm intelligence algorithm, as well as for the different infill pattern techniques, so what happened, the component prepared very nicely. So compared with as we know about, compared with A, B is a better product by adopting the different AI techniques. Okay, then these are the common that is that product failures occurs, like delamination, second cupping blowout. So these are the improper defects which are existing in the system. Then these surfaces which are, we call it as ragging. And for print not sometimes sticking to the bed due to some temperature differences. And for layer not perfectly worked out, therefore layer separation, one of the defect. And for brittle resin also occurs in this zone like this. And for residual stresses produced, so this is very important issue in the process of which one, that is additive manufacturing process. Then looking on this warping and for resin blockage sometimes, and most of the situation, if you look at your same images which shows the more porosity, so that will also will look, and residual stresses more important. And for cracking, post processing things are needed. These are the some of the common coinable that is defects which are exist. Then apart from that, further we see here shrinkage and the nozzle clogging sometimes, and the delamination and the curling, then for wrapping. So many kind of things which are exist, last row on banding, cracks, and the poor bridging. See why this happened, because of the temperature of there are so many factors, as we know already discussed in our previous session, and already we learned from our theory, the printing process parameters. If you take any process, so in order to minimize this, so what we do, we are not interested to that is develop wrong product. We need to develop straight away a good product in the first stage itself. So over to that, there are some challenges in this. So looking on the circle, compatibility issues, and for second one that is processing difficulties, and for shrinkage and wrappage, and for material degradation, adhesion problem, and the material consistency. There are different subtopics exist. This is only we recap from this 3D manufacturing process. So material inconsistency is if you select improper material, mean there are certain issues will exist, like previously what we seen different error. Then we are targeted here to produce best of component here. One of the biomedical top that is image represents here. So through the additive manufacturing process, we are ready to prepare. Already process started here. Some industries on preparation of the heart valves and the blood vessels, skins, bone, cartilage, and many more things. So our target here, artificial bio components, we need to produce it. Here the strength depends upon your cross section of the infill pattern. So this is what our main target, our topic of this. So how we minimize this? So this is one example to improve the strength by adopting the different patterns. Then likely looking on, this is another one more component. So here also that component produced in the real time to which one our additive manufactured component. This is for our lungs, towards the area, throat area, so where we can see here. So in this area, waste, if we produce wrong component, means again the component wasted in the beginning moment, because cost wise directly connected here. So in this point, based on these examples, so we go on this area. As we look already, most of the publications and for textbook, you can see these are the different parameters directly invoking on the product, that is quality, like layer thickness, and for raster width, and the comparable examples of number of contours, raster angle, and for air gap, raster width, contour width. These are the many more tool path parameters. And for your build orientation, so build orientation, how we are locating the part, XY oriented, YZ oriented, or XZ oriented. Here that orientation much more important. You can see that second one. And the third one, more important among all, infill patterns. So this is our area. So here we need to fill some kind of some patterns. For example, most of the products selected here, rectangular pattern, grid pattern, then triangle, and honeycomb. There are different structures here we use. So this is our concentrating area to minimize our waste here. So we go on the different infill patterns used on the 3D printing specimens. So start from the like cross 3D, and for cross there are two differences which will exist, and for cubic subdivision, and for cubic again there are certain differences, and for grid commonly we know. Then gyroid structure, and for lightning structure here. And for this is commonly we prefer the lines. Then these are the set of examples we used for the different infill patterns. So commonly zigzag, triangle, tri-hexagon, so cubic, offset. So like that they given the different infill patterns. So here, if we improper fulfillment, if you using means the product, it won't get the efficient strength, like impact during the impact test, or maybe a tensile test, or maybe on any other test if you carried out on this. Therefore selection of the infill pattern much more important to minimize the waste. Okay, then you can see these are the other way of representation. We are looking on the cross sectional patterns of this. Okay, so the two-dimensional way, that representation of cross sectional views of the structures. See some of the component here, you can see this. Okay, so the start from this one, the rectangular block, so that is square block, and the square block connected with some lines here, and further strengthened. So like this they modified. So you can see that the common example, tire threading operation. For making more friction, we are using for online as well as offline vehicle, that tire companies, they recommended different kind of patterns to make more friction, more gripness. So like that, in order to improve some mechanical properties, so we to adopt the different kind of common things here we exist. So I think this strategy is almost currently using by the different production process of the additive manufacturing component. But we go for further advances because we are not ready to use for conventional method, traditional method like this. So we go for some advanced level component. So just you look on this. This is like woodpecker design. So woodpecker normally the nose more harder in strength. So from this the pattern selected for this, just you can see this image how that the component, the same image you are looking further. I think this is the that is D image. You can see this, that the image, the cross sectional behaviors of the woodpecker nose they designed, and based on that the 3D model were prepared for this. So this is one of the good idea for designing a infill pattern. So it is a good method. And go for previous one, arch woof shape. You know, normally just this is advance of these models. Just you can see this arch woof, you know, the shape further fine-tuned by the different models. So accordingly you can see the three-dimensional model of this for making the different infill patterns. So this pattern, we don't know whether which one is more strength or which one is more weak. So by performing the experiments only we can get it. So all the patterns which are gathered collectively from the nature from the inspired techniques. This is what much more important. So instead of the normal conventional patterns. Okay, so just you see this is the production process of this one, how the component prepared for this which one, sir? This is arch woof shape. And we seen on this woodpecker design much more important. Woodpecker normally, you know, that it contains more impact strength, the structure. So hopefully the most of the researchers they prefer this structure for production of this. And we go for next inspiration here to minimize the waste by utilizing the cross section of the that tree root. Okay, so just you see this here different tree root that cross section you can see here, number 1, number 2, number 3, and number 4. In my research work also I used the same different pattern like gyroid and honeycomb pattern I selected for my research work that I'll show you in the last of the session. So here you can see this, the different color patterns, number 1, 2, 3, increasing of compressive strain compared with the stress strain diagram. You can see the different observations of the different infill pattern structures. So compared with the traditional one, this one naturally inspired biofill pattern, which will increase the more strength as well as the less weight and more strength which are existed through this plot. So compared with this another graph here, density by pressure value for the structure number 1, structure number 2, structure number 3 and 4. Similarly for density, energy density plot here, just to compare with this, one structure here produces very higher value, I think second, whereas in this third structure which is producing the higher amount of energy, so like impact strength. So from this we observe that as compared with the conventional one, this one produces the much strength onto that. Then looking on this plot here, there are stable under the 95% of the strain also, as well as you can see here compared with Young's modulus and density, 3D printed super elastic materials on this work, which is lying more than the above of the traditional super plastic materials like this. So this is the example which we used the general representation of the standard compared with the standard infill pattern. These infill patterns mostly adopted recently by our researchers. And another one more that is inspiration from this fish surface. Just you can see here, this is that closest view of the outer skin of the fish surface. So that is looking through the same images how these are the flocking existing over the surface, the same component which are produced in the 3D infill pattern which we used for our process. So this one sticking more and the deposition of the material in best way. So like that for these purposes we prefer this fish based that is infill pattern behaviors. And you can see this is from the different tree plant widely used for the infill pattern. Just you can see on the first row from this plant that the same images we are looking. So that views of component where we prepared for this. So I think these are the small like spine like structure, which increase the more strengthened, and between the layer, the raster behaviors are also good like that. I think you are reviewing on this biomimetic process of this, how we prepared for manufacturing the additive manufactured component, how we are preparing this. And moving over next one, that is web fort structure. So like this, from this one bird, so you can see the different bio inspired sealing disc. Okay, so sealing disc which are prepared through the cross section of the 3D printed specimen. So instead of the others one, so this way we design is somewhat good and more strength. This is the overall conclusion onto this. And again, one more inspiration here, like water spider and diving bell. So there are the two examples that preferred here for preparing the better infill pattern here. So compared with these kind of infill patterns like this, and like this different pattern, these are producing a good amount of the that is impact strength, as well as tensile strength, as well as your mechanical test commonly we consider here. And for elephant nose, this structure more robust structure, so we can rotate at any 360 degree. So here that shape of layer which are produced according to the component. So this is from the elephant nose, the current research going on in this field. And another one structure of the one kind of beetle. So beetle structure, outer layer more harder. So from this 2 micron view, if you can see this that granular structure of this one. So this kind of infill patterns also another kind of opening of research for compared with the traditional one for improving mechanical strength. You are looking on 200 nanometer microscale on the view of the single granule. And the next one, we go for the whale, humpback whale and bowhead whale here. So looking on this, this structure is too hard. So that we prefer these sections here for our infill pattern structure. So where you can see this comparative statement of stress strain curve diagram. So if you take the different cross section at different places, that researchers tried to show out the different output. Okay, so I think this cross section which shows the more strength as compared with these different patterns. So this is also another one more bio inspired infill pattern techniques. And another one from the plant, like bamboo tree structure, so circle wise design. And for sometimes fish scale also we prefer, like that previous fish different, this fish surface totally and different, because in this case compared with the bamboo and fish scales, just you compare this two circles are just touched, but here make more closure to generate this one, that is overlap one another one. Then we go for the crocodile structure also, this one. So as compared with all, that means adding of all these structures, bio-inspired unit cells are produced. So like that, that structure produced for making more infill strength. So dear attendees of these professors and students, so here research scholars and students, just you see this structure compare with the previous structures of this existing structure used by the different authors. So we can see that different observations we can get it by doing the different activities. And from this this one more things we will select the design from this. This also another kind of better infill pattern, and you are viewing one from the component of this good amount of one. And the second one from this pattern also we received, because these surfaces too hard to make good fine structure to get the more impact strength of the one. Okay, and next one here again for some three examples of a component, a bionic object like bone, and for wings of butterfly. Okay, so just in case of bone cross section, we select this is the infill pattern. So this is the bio inspired model. These are very difficult to structure our model, but most of the researchers are trying to attempt to produce such a kind of things nowadays. Again, looking on second column, wings of the butterfly. So butterfly wings like this at 1 micron. This is the infill pattern structure like this. And next one for the L. Famsona, that is another one kind of fruit. this fruit structure totally are different. This infill pattern, like similarly mimicking to the our normal honeycomb structure, but here pentagon or hexagon structure which are pentagon structure which are exist. So this also another one kind of infill pattern we use for our purpose. And the Norway spruce is another one variety. So just you can see this the structure of infill pattern like this. So while adopting these things, our waste must be minimized and increasing the strength noted by the different researchers. Then you can see this another variety of insects. So these structures are truly hard, So in this structure, scorpion structure here, you can see this the observations of the structure totally on different. Then here also tree root. So we estimate normally tree life based on looking on the different cross section. So that profile also we used. And another one, this is another insect. So normally changing the color normally. So here the structure also changed. The researchers mentioned here, when it is relaxing situation, this pattern occurs 200 nanometer. Then for existing that exciting situation, that pattern occurs like this. Dynamically the pattern change, the change of colors of this that is insect. So this is also another one variety of infill pattern structures. And for this is another insect. So mantis shrimp Tesla inspired bidirectionally panel here. Just you can see this end somewhat coarse structures which are exist like a fly in manner. So these structure which are produced for the infill patterns. So similarly we are looking different cross section for the other insects also. This is spiral behavior of things exist. Okay, so these structures are which shows the more strength as compared with the traditional one. So which means that we effectively utilize the resin for manufacturing the component as compared with the conventional method. Okay, so if you are, I think you familiar a lot onto this. And now we are coming to the part of which one we are the designer to identify the different structures, nature inspired strategy if you want to follow. This is the common rule of thumb. So for example, we are going to design a flower like infill pattern like this, and we can go for this route to prepare this. And for this, if you want to add some, these flower lines are too straight, so you want to do some slight modifications in this route. So you can go for the first define, this is what your design challenge of your infill pattern. And for biologists, how this is compared with your existing one. So discover, so humpback well backside the tail, it shows like this normally. So biological strategy discovered from this. Then studying then bring this product, like abstract the component like biological strategies on this end. Then we adopt this product design category of infill pattern like this. Then finally the component suitably modified according to the design. So by adopting these are the strategies, we minimize our waste to maximum. We that is use our PLA or ABS, any kind of materials more effectively, we utilize it. Otherwise, what happens? Product defect occurs. So again, we go for the reject the component. Again, we go for the recycling process in order to avoid this. So just some of the examples I recommended here. So for adopting this kind of infill patterns to prove the better which one mechanical strength. How we adopt these kind of techniques, like how to minimize this waste, how to design this component. For example, how we design number of holes, the distance. So we go for this example normally, that tool path parameter and cross section infill pattern dimensions. How we that is prepare, how to do model like this. We go for the swarm intelligence algorithms. So the professors and research scholars and the student, you must aware about, first of all, before going to the part connecting to your machine, that is swarm intelligent algorithm. So this is the general plot which is showing the whether maxima or minima problem. Just you can see this curve which is going on the different path. So where we can see here, this is one peak, and this is second peak, and the third peak, and the fourth peak. These are the 4 peaks are exist, and here there are 3 valley points are exist. So these peak points, whenever reached by the system, that is called the global maximum value. and remaining all other peak values, these three peak values referred as here local maximum value. So this is what local 1, local 2, local 3 and global maximum up. Local maximum 1, local maximum 2, local maximum 3, then global maximum value. Similarly, we see here local minimal value number 1 and local minimal value number 2. As compared with this is what global minimal value. Just you see this compared with these two values, this value only very lowest one reached. Therefore, this is what global minimal value. So that is what our target, to find the either global maximum value be to attained or maybe global minimal value to attained. So just the author specified here, for example, shake off some example they mentioned here. These are the solutions which are produced with reference to the x and f of x value. These are the local maximum value of your solution. Conventional approaches like traditional approaches like engineering mathematics based, iteration based calculations always trapped on only on local maximal value or local minimum value. So in order to achieve to reach our saddle points from this place, from this place, from this place, escaping these places to reach on maximum global value, the swarm intelligence algorithms are widely used by the different researchers. As a mechanical engineering field, not only for this, for all engineering field, widely used for the different applications on this swarm intelligence algorithm, which are naturally inspired based techniques. So we call it as here meta heuristic algorithms also. So we go for example. So just I told you just previous of my slide, this is old model method. So we go on a trial and error basis. Level 1, okay, not satisfied, then we go for to bound level 2, level 3, like this we go for escalation process to perform to reach the optimal global value or global maxima value, global minimal value, whichever you want. But we can go for instead of this technique because more weakening and time consuming process. So that what we do, we go for the new model of swarming process. Swarming in the sense bird flocking, ship swarming, like this. So in this pattern, completely randomized process. So wherever we can go through the randomized process, we will achieve either in the black box of higher value of minimal value and the higher value of maximum values we obtained here. This is the comparison better to understand why we go for the swarming models. Just this examples of referring in 1970s itself started by neural network for predicting the different outputs here. Then afterwards in 1980, the genetic algorithm is the mother of all algorithm. So genetic algorithm almost nowadays matured, but till the people are using this algorithm. Then ant colony algorithm, then DEO, differential evolutionary algorithm, PSO, then artificial bee colony algorithm, then IWD, that is intelligent water drop algorithm, and many more algorithms coinably added by different amount of researchers. And latest one in 2020, dolphin swarm optimization algorithm. So this algorithm widely also used by the researchers. Why we use these are the algorithms in the sense this is the comparison. For example, there are the different parameters like range, means here only on traditional algorithm only to find the local search, not for global search. But you can go for nature inspired NIA or one among the swarm intelligence algorithm, which always to reach out which one only on the global search and does not trap into the local values. And for randomization process in traditional algorithms, always deterministic, no use of random number. But in case of these algorithms, we always stochastic in nature. So we may use the different random numbers and the different random walk strategies like Levy flight, opposition based strategy. There are many strategies we may adopt to produce the better value to reach out the our saddle points from local value to the global value. Then scope here, this is only the limited and our problem specific. Here there is a black box approach like a wider scope. That is a black box in the sense we don't know where is our optimal point. There is a wider scope we can achieve to reach the global search. Then gradient free optimization, this is one more that is incapable to deal on discontinuity problems, multimodal and nonlinear problems. But this will cover all your gradient free efficiently to handle your problems, maybe on discrete in nature, maybe on non-linear, maybe on unimodel or bimodal or multimodal. So whichever the model, these algorithms are performing a better one. Then this is what the different varieties of swarm intelligence algorithms widely used by the different researchers, taking from the plant, maybe a tree plant, and for different insects, and for different animals, and for aquatic in nature, and for this is the forest related animals like from camel, elephant, humpback whale. So lot of examples based on these swarming behaviors, the authors were developed different algorithms. So I am showing one paper relevant to this, which was published in Swarm and Evolutionary Computation in the journal. I will share you after this. So performance assessment and the exhaustive a listing of 500 plus nature inspired meta heuristic algorithm. So just you can see this paper that authors were tested normally by some benchmark suit here. The author chose here CEC 2017 benchmark. I think just I'm scrolling down. The authors, they mentioned here the scope of the publications in this. Just I'm roughly moving over there. Just you can see these many number of algorithms now, at present exist. So started from the 1960, then gradually increased these many algorithm 2009, 2011, 2012. Just you can see this around this one ended by 2022. So dear attendees, please refer at least to one paper for if you maybe you trained already. Some of them, those who are attending already, you trained on these algorithms. So if you are in this stage, please develop some new kind of algorithms. Those who are not trained, if you are in first level, you start one algorithm to work by adopting any kind of engineering field, especially for that is additive manufacturing process. So these many number of algorithms coinably published by reputed journals. Just we will see some few part in our lectures. So this is the example of these algorithms used. And for these are the common, again just I pointed out some from, just you look on from the bottom itself: Gasly optimization algorithm, Grill Herald algorithm, coral reef, that is one kind of flower. And for serval optimization algorithm, Starling murmuration optimizer. So these are the recent grasshopper, elephant herding, honey badger, moth flame widely used by the different researchers. Okay, sir. So like this, you can refer for your purpose of your research. You will utilize for this. And for more specifically, I am going to talk about these two algorithms. So one on the humpback whale strategy. This behavior utilized by the swarm strategy of the humpback behavior. So that we, based on that, the authors developed the algorithm. In our process also we utilized. This is this image, the blue color bordered image, which shows the gray wolf attack of the particular object like a cow. You can think on this. So there are the gigantic, the small gigantic gray wolves are reaching this place of this one by using the different strategy. And moving on B, how they are grouping to attack, and the grouping attacked may be in another direction and another direction. Then finally this is the escaping direction because of the good strength produced by this, which one, this like cow. So because of that, the objects are deviated. You can see this like the images of the foot parts of the gray wolf. So using this different strategy, that swarming strategies, the algorithms are developed. So moreover, I am going for specifically on like which one, humpback whale. So this is one kind of spiral strategy which is followed by, that is produced by our humpback whale. So just these colorful bubbles produced by this humpback whale. So all the small fishes are attracting this spiral behavior, and because of this nature strategy. So based on that, all fishes are coming to this place of this zone. So this domain, body or continuum, automatically that humpback whale ready to eat the good amount of the fish here. This kind of strategy, good amount of strategy. So one researchers used for this to develop the algorithm. Just I am going to show one video onto this, one or two more videos. Very sorry.
Sir, audio is not coming.
Yes, sir. Sir, audible? Hello?
Now it is audible.
Okay, sir.
But video audio is not coming, sir. What you
Okay,
are said.
okay, sir. Thank you. I'll tell.
Thank you.
I'm telling now the explanation onto this. So in this video, that researcher says that the bubble net formation of the which one that humpback whale. So based on that, the researchers developed the one algorithm. This algorithm developed by the researchers Mirjalili and for Lewis. So why I preferred this in the sense. So this paper alone reached around these many number of citations, 14,495 citations achieved only on this behaviors of which one this whale optimization algorithm. So if you are interested, you may go for to modify this algorithm something for your purpose too also. Just a minute, sir. Okay, so this is the algorithm. So very known interest our closest researcher. So we are working to this professor also Griffith from this Griffith University, and there are the different algorithms given here, and this is the representation of the bubble net feeding behavior of the humpback whales. So the general inspiration of these algorithms so started from this which one, sir, the killer behavior, how to generate this. See, in any algorithm there are two things are required, one on the exploration phase and the second one on the exploitation phase. So exploration in the sense, just you can identify in any algorithm there is a domain. This is our domain here. So we are in the point to reach here, this point. So what we do in this situation, we landed over in this point. So this is called exploration. So after exploring this part, what we'll do, we use some different strategy to reach out to the places. We use in the black box in the different strategy to reach out to this place. So this path route referred as your the meaning of exploitation. So in any algorithm testing purpose, always we need to develop exploration and exploitation plots are must, and the diversity of different solutions are also must. So this is the point, exploration point, and this point as the exploitation point. The authors represented that in the algorithm, like which one, always we start from this algorithm, like some standard procedures we have, formation, that is a number of worlds present and the world strategy, all those things they implemented by in terms of the equations. So the physical behavior of the system we try to convert into the mathematical model. That is very, very important. So by the way, the authors developed some behaviors they represented in terms of the 2.1 and 2.2 equations, the current iteration, how the best solutions are moved from this one. And these are the further strategy for making better exploration and exploitation phases. The authors used the two different vectors, A vector and C vector, for that is for better performance. So the authors given illustrative behaviors of this. Then the bubble net attacking method, the author says here, for the exploitation phase. So like how that things are prepared. So the authors prepared by the two-dimensional position as well as the three-dimensional position. So here xy alone exists in two-dimensional, whereas here xy z also the three-dimensional position they constructed. The spiral behaviors, the authors represented the bubble net behavior, they represented like this formation. So likely that r value 0.4, that is L value ranging between the 0.5 to 1. If you want to interest, you may increase this dimension also, whichever you want, the spiral updating method. So likely the author mentioned that the point number during the exploitation process, shrinking the encircling mechanism using the 2.3 equation like this. And for second approach, the author used here spiral updating position. So here you have the chance to utilize to adopt any kind of new strategy for modifying this algorithm. Then you put your own name of your algorithm. See, for that I am recommending the sample of example like Levy flight strategy. So this strategy widely adopted by different that is researchers. So you may utilize this Levy flight strategy if you adopt mean the system go on further insights of your one. So this strategy widely used by the different researchers. So random walk methodology or maybe on Levy flight strategy or chaotic methods. There are many methods are available. Chaotic methods, there are many methods are available. Just if you introduced for this for algorithm testing, different chaotic methods which are available like a cubic behavior or square behavior, whichever the behavior if you adopt the procedure slightly modified by you by adopting some strategy like that. If you take the chance to utilize which one sir, this spiral updating position. For example, here you may adopt one more Levy flight strategy formula. If you introduce, automatically that exploitation fine tuned to reach the best result. That is what I am conveying here. And for next strategy, once if you completed this entire process, sorry, once in the entire process completed, again we go for the exploration phase. So once we completed that exploitation, we go for the exploration phase also. So there is no unique strategy to follow exploration and exploitation. You may use either exploitation and the exploitation, that is your wish. See, in fact, in the situation, search for the prey after generating the bubble net, search for the prey referred as the exploration. So there are some deterministic method we used for performing this action. So likely the author mentioned that the pseudocode of this. Respected professors and research scholars and students, if you are already trained, maybe some of them, I don't know, I am in black box to looking on all your experience, I don't know. If you are sir, I am not trained this, but I am more interested onto this area, means you develop this first of all using, nowadays a large language model existing like ChatGPT, DeepSeek, Monica AI, U.com AI, Clad, whichever. You may develop your own MATLAB code or Python code for generating the algorithm. So like such intelligent method, if you prefer, you will get some much more idea onto this. So in this case, for the pseudocode of this algorithm, always in all algorithm initialize the population. So here we use for the whales population, calculate the fitness of our each search agent. So in our case, the search agent, for example, our infill pattern, for example, I'm going to take for this example of this. So infill pattern here, where we go on to produce the component in this case. So this is our lower bounds and upper bound for the x direction. This is for y direction, lower bound or upper bound. So which area you want to go, so likely you decide by using this fitness function calculations. Sometimes the fitness function may be on image file, sometimes the fitness function may be on mathematical equation. So most of our mechanical related or any core engine related, the fitness function in terms of some mathematical equations only. Then for extra referred as the best search agent. So among the which one is best, see for this we go for normally in our home we are calling a crow for feeding the food. Someone may come and take even nearby, someone get fear. So which one come nearby our means, that is what best way to catch the food. But some fears getting some crows getting fear, so that far away from that point. So like this we understand the best search agent. So here agent in the sense you take any one, like any one of the animal, any one of your swarm related component. Next always we start with while. So you need to set that whether number of iterations maximum or attained your objective function maximum. So this author here they specified number of iterations. So once your iteration set in this pseudocode, then for the search agent, search the best agent, then update the different parameters already authors they mentioned, like a, small a, capital A, C, L and P value. Then the author takes that here whenever the probability value point less than 5 if condition 1, again modulus of A less than reached 1 if condition 2, update the positions of the search in the equation 2.1. So where the author mentioned in the point of 2.1 here. Okay, so in this equation, so all the equations modeled by MATLAB code or maybe on Python code. So accordingly the program generated by the large language model, because we are most of the people nowadays they are using code generation using this LLM model. You also to prefer this. And for if a greater than or equal to 1, that is 1 means, then they select the other route for this random search agent, and for position of the current search agent using the 2.8 equation. So like that the algorithm simulated. Say how the random numbers are generated in this. Normally we go for generating the random number, we use this function normally RAND. So I used for my most of my research work using this. Whenever I am writing a code, always I used to prefer the random number like this. I take any one column to feed in the MATLAB, embedding in the MATLAB code to yield the best search agent. That is what here that the author mentioned. And the current search agent using equation 2.8. So using this dot product. And like that, the program is over. Program is closed after that means which Ambak will eat the maximum amount of the food. That is our main target, which achieved the global maximal value or global minimum value. So corresponding output shown through that our screen, and that program ended with the written X star. Here number of iterations increased until by setting of your number of iterations maybe on 200 or 400. Like that the pseudocode explained that is given by the author. The author tested, sir, if you develop any one algorithm, so you to check with some standard like functions, benchmark function, unimodel and bimodel and multi-model. So I go with that some further slides for explaining this. See, yes, unimodel. This is what unimodel. Sphere function referred as the unimodel because global minimal value here. And this is Rastigian function called another one more test function that is called Rastigian function. You can see the many peaks and many valleys which are present. This is Rastigian function commonly used by the researchers. This is multi-model problem. This is mini-model problem. So either genetic algorithm, PSO, or maybe on Salsam optimization algorithm, lion optimization algorithm, water cycle algorithm, moth flame optimization algorithm, monkey swarm optimization algorithm, whichever algorithm the authors, researchers developed, they must test with this sphere function and other function test. Then some of the functions like Michael this function, one sample function here, drop wave function, complete one function test function exists. And for Rastigian function for 2-dimensional model and 3-dimensional model, and the Damavendi function, this is another function. The peak point, the valley point not exist at the center of this, the valley point exists somewhere from out of your point. So this function refers to Damavendi function. So based on this, that professor written the tested by the standard equations of this whale algorithm. For the tested by multi-model benchmark function, here also then fixed model. So authors like that composite benchmark function, like that. So these information available already our internet, like you can get it from MATLAB or any IEEE or somewhere. Ackley function, Rastigen function, like this they given. So authors are verified all the humbug whale, that bubble net procedure. So they compared with the PSO. Then for GSA, DE, FEP algorithms, they compared the value of which ones are, that is optimal value, average and standard values they obtained. Likely the comparison always goes like this. And they plotted so many for iteration. They set by all function 1 to function 20, set by constantly on 500 iterations. Like this they compared. I think this algorithm, they saying that produces better results as compared with that. Further fine tuning of our exploration and exploitation behavior. Further, the author tested by some common mechanical problem. This is common for any algorithm testing, like mechanical spring. Okay, for the compression string problem, like PSC design data book or any design data book, if you prefer, this is the general equations are available. According to that, that author tested the WOA, and for the GSA, glow swarm optimization, PSO, like this they compared. Then they saying that WOA here, PSO, GSO, glow swarm optimization algorithm, as compared with that, standard deviation reached 0.003 as compared with this others of PSO and GSA. Like that, some classical engineering problems solved. This is the spring problem, tensile and compression in spring design. And for welded beam design problems also, this is the data book based, the author preferred. So our target here, minimize the x1, x2, x3, x4, the subject to the constraints given in the problem. This is the complete problem of the welder design problem. After adopting this strategy, optimum values of HLTB obtained for the profile of this one. The author significantly mentioned in the diagram oriented. Then cost wise, they compared with that 1.783 reach. But likely all authors preferred developing some algorithms. Some algorithms sometimes weakening. Just you can see here 1.7304, but unfortunately improved harmonic search algorithm reached 1.72. So just from this our conclusion, none of the algorithm better than performance other. This is called no free lunch theorem. We don't know which algorithm perform because we entered in a black box. So that this switch in this welded optimization problem, that is near to the value of 1.742, but anyhow this algorithm in this improved harmonic search reached better results. Like this the author compared in this fashion. And looking on this, PSO yield better result as compared with the standard deviation of the WOA. So like that, the author conducted the different mechanical classical test. So this is compulsory, must perform. Author finally they recommended that this algorithm produced the different varieties compared with the different behaviors. The author mentioned here encircling prey, bubble net foraging behavior for the humpback whale. So extensive study was conducted, 29 mathematical benchmark function. So that author says that this is the work developed for after testing of the some 6 structural engineering problems. One of the swarming behavior of the whale optimization algorithm. So these are the some of the examples you are looking on the testing of which ones are that humpback whale one. Okay, now come to the point. So once we trained one algorithm, so if you are in new in this area, start to develop one algorithm, read one paper and develop the algorithm using large language model. Test it in Jupyter Notebook or Google Colab or MATLAB, whichever you are interested. Then do the 500 or 400 times of simulation. Once you trained, then you do some slight modification, like adopting the chaotic strategy or Levy flight strategy, opposition based strategy, any other nature inspired strategy. If you adopt, then that value further fine tuned, then you publish one Q1 journal relevant to your field. So this is general rule of methodology for setting any algorithm. So setting initial control parameter in all algorithms, some control parameter will exist. Then begin with always iteration equal to 0. Initialize the agent or maybe an candidates. In case of crow search algorithm, crows are my agent. In case of whale algorithm, humpback whale referred as my candidate or my agent. In case of fish farm algorithm, fish my candidate or maybe an agent. Then evaluate the initial candidate whether best fit or not. Okay, then next, for while not termination condition, do each iteration to increase to find the new candidate or new agent, evaluate the new agent or new candidate. If the newly evaluated candidate best means, then you proceed for the next iteration. Even for the next iteration, if you don't use the same kind of control parameter, you update the control parameter, then to reach out to the end. If this is the general rule for developing the swarm intelligent algorithm. So this is what they given in terms of the plot, like define the algorithm plot and initialize the search agent like monkeys, lions, or maybe on tortoise, or maybe on orca, or maybe on humpback whale, different search agent, and define first termination criteria, maximum number or minimum number, or maybe a number of iteration. Then evaluate your fitness function, then update the search agent, then generate the optimal solution here. This is the way that easiest way of representation of the flow cycle of a swarm intelligent algorithm. The fitness function here, your mathematical equation. In case of image processing of additive manufacturing process means images referred as your input. Okay, so this is general idea about the swarm intelligence algorithm. So coming out my part of my research work, so this is FDM mission, so where I carried out the experiments at industrial type continuous production mission Indo Taiwan Stanley India Limited, that is the company located in Oragadam, Chennai. So in this company I conducted some of the experiments relevant to this on fabrication of the bio inspired which ones are that component. So this is the flower based one arrangement. The flower cross section is a biologically we referred through the same analogy, likely you are looking the structure here. So this structure mimicking on the combination of gyroid and which ones are honeycomb pattern. So instead of the common pattern, like this, so we preferred here which ones are this kind of structure. We prepared the model, and based on this, the cross section based that components are fabricated. These are the components which we are fabricated. Likely I'll show you some physical component here for your reference. Some of the component we fabricated, so demonstration only this possible. So the components we fabricated, so in this fabrication, for example, the pattern here, likely you can see here this pattern we are preferred here, gyroid and that honeycomb pattern we preferred in this FDM machine. So in the settings we preferred converted, the normal process of this one. So based on this our components which are produced in this machine. I hope you understand this. This is the photo of image shown in this picture, how we prepared. Then mechanical test conducted. Then for surface roughness and for dimensional deviation, compared with the CAD model also tested. Then the semi analysis we carried out. You can see this some voids, triangular voids that is generated during, because in any situation these are the common things which are exist. Just you compare the both same images. Then we adopted here some kind of techniques like improved whale optimization algorithm. So already one author developed whale algorithm, so I preferred here improve something by using the Levy flight strategy with weighted 0.5 weighted strategy I used. So after adopting this, existing material produces, this is the cross section, that pattern. But after adopting this that kind of our algorithm, this pattern which is noted, so I think some differences you will observe here. The gaps completely minimized, not completely minimized, some slightly some surfaces which are modified. Just you can see this tested in the same machine also. And based on this the work published, our surface review. Yes, so this we will discuss. One minute. as you are viewing this, enhanced surface quality and strength of FTM specimens using. I used here for converting mathematical equation design of experiments approach, box bucket design I preferred, adopting with bio-inspired algorithms. So I preferred here for my research work, I used here Dasmanian devil optimization, and for Remora optimization algorithm, and for tuna swarm optimization algorithm we preferred. So the paper published based on this experimental work, the paper published, and the experiments, the real-time specimens, CAD model, and the component where we tested how we fabricated, and for converted into mathematical equation, and for the same behaviors, the fractography analysis, that flower based lily flower based that gyroid and that shape, and we implemented it, that algorithm. This is one kind of swarm, Tasmanian devil, so more dangerous one. And for next one, another fish, remora fish we consider. These are the algorithm developed by other researchers, so I got permission from those authors to utilize this algorithm for my research work. So based on the after getting approval, images, copied images, all those utilized in our paper, and paper published in good effective way. Then we implemented in this MATLAB environment. So in this sense, you can see this, I think TDO produced a better result as compared with this ROA and TSO. So you can see this from this, there are different routes which we identified. This is the convergence plot of the objective function. Somewhere you can see the exploration and the exploitation slightly modified, and somewhere then finally reached the transient states to steady state conditions of this algorithm. The paper published, and finally obtained our results, and best case algorithm, best case and worst case result, and average and time taken, and for success rate of the algorithm verified and tested, and paper published this. So this is what the paper, one paper relevant to this work. Then further we are continuing for adopting the different algorithms, and we are developing, working with which one means machine learning algorithm like XGBoost, NGBoost, CADBoost, some assemble and non-assemble algorithms to improve further onto this. And our team of work, one more paper, that is one paper here we adopted, that is not additive, that is India laser cutting, which is published in Materials and Manufacturing. We adopted in this process which one means WOA, whale optimization algorithm, we preferred here to perform this optimization work. So the same whale optimization algorithm we used for this one purpose. So likely I hope all of them you understand, and someone you familiar on this area, some slight technical things you noted, and for others, those who are new, I given some little bit of knowledge in this area. So thank you so much. Hello.
So my sincere thanks to Dr. A. Tamilasan sir for the wonderful presentation. Now the session is open to the audience to clarify your doubts. Participants are requested to clarify your doubts. Sir, can you see the chat box, sir? So,
Sir?
can you see the chat box?
Yes, sir.
Yes. Yeah. A doubt from Abhishek Kumar Gupta, sir.
Yes, sir. Thank you for your good question. Yes, that also we will do that using by tuning of the tool path planning, that planning to be estimated through this different algorithms we may utilize it. But for this I recommend ant colony optimization algorithm, which is widely used by the different researchers for performing the better tool path, not only for this EAM, for advanced machining process like ultrasonic and abrasive water jet, whichever the process. That also we will support, sir, to reduce the usage also. Further, my recommendation, ant colony algorithm further added with boosted with for better exploration exploitation point of view, boosted with some machine learning algorithm, just some algorithms like xg boost, ng boost and lstm. So many algorithms also we will prefer for fine tuning of this. And one more, I hope this answer may suit for this professor, and I hope the screen is visible to all. So I am in the field around 10 years in this field. So I am thanks to my guru Ravi Pudi Venkatra, who is that professor and head in NIT Surat, in Chinchana, Surat. So the professor developed so many algorithms. According to our guru direction, we started to work. So based on that, my field of experience, I also developed one algorithm on the testing stage of this GAL-MIDGE optimization algorithm, which is posted in our MATLAB website. I tested only one function. So very soon we will publish work in this area. So like this, if you are interested, you may develop one algorithm for developing your which ones are on preparation of your tool path planning. So many examples we have. So I think based on this title, according to the question, I recommend that is Journal of Production Research, Taylor and Francis, sir, for better publication onto this area. Thank you so much.
Participants, any other clarifications?
Thank you so much, Anita madam. Yes, sir. Surely, surely useful for essay-based optimization, because we are in industry. We are slightly not adopting the till on industry 4.0. If we adopt definitely a full amount of which ones are like industry 4.0 and moving towards on the transition from 4.0 to 5.0, definitely the in industrial area the minimal waste to be achieved by adopting this swarm intelligence algorithm. So this company where I worked out this, Stanley India, they are the manufacturers of which one? They are the manufacturers of mobile screw manufacturers. Okay, so this is the Taiwan-based company. In this company, very soon, not introduced in India, they introduced in Taiwan, adopting the different AI introduced strategies for minimizing the waste by including which ones are adaptation of the 5 years techniques.
Any other clarifications from participants, sir? Yes, sir. I think no more clarifications from participants' side.
Okay, sir. Okay, sir.
Once again, I thank you very much, sir. My sincere thanks to Dr. Thamarasan, sir, for the valuable presentation regarding the swarm intelligence to minimize the wastage in additive manufacturing. Thank you very much, sir.
So thank you very much, sir, for your. Really, I never expect in this forum, because there are many peoples in this
Yes, sir.
FDP process. I really happy. So I will again come on. I think last day of last session. Yes, sir.
Yes, sir.
So further that time I will simulate codes for your better visibility of the real-time situation of the additive manufacturing process. So thank you so much, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you very much.
Bye, sir.
Yes, sir.
Sir, shall I
No.
end
Yes,
with this?
yes,
Okay,
yes, sir.
Thank you. Thank you.
Now the session 6 will be delivered by Indian scientist Dr. Chanchal Ghosh, sir. Sir, welcome you, sir.
Thank you,
I'm
sir.
really
Am I
proud to
audible?
welcome. Yes, sir. Audible, sir. I'm really proud to welcome our expert for the session 6, Dr. Chanchal Ghosh, sir. Scientific Officer, Indira Gandhi Center for Atomic Research, Kalpaka. Dr. Chanchal Ghosh has been serving as a scientist at the Department of Atomic Energy, Indira Gandhi Center for Atomic Research, Kalpakam, India, since 2008. His research focuses on physics and structural transformations in metallic and ceramic systems, including ordered intermetallic and oxides, using electron microscopy and electron spectrometry. Dr. Ghosh earned his PhD from Homi Bhabha National Institute, IGCAR. Subsequently, he has joined at the University of Connecticut and Sandia National Laboratories, USA, for postdoctoral research. Dr. Ghosh has made significant contributors to the field with approximately 60 publications in peer-reviewed journals and books chapters and over 80 international presentations. He received several honors, including the Young Scientist Award from the Department of Atomic Energy, Government of India, Excellence in Microscopy Award from the Electron Microscopy Society of India, and multiple best poster and oral presentation throughout the world. I welcome you, sir.
Thank you, sir.
Now I kindly request Dr. Ghosh, sir, to start session 6.
Thank you, sir, for a nice address for this part. And at the onset, I would like to thank the organizers for inviting me and to deliver this talk. And also, I'd like to take this opportunity to wish everyone a very happy Vinayaka Chaturthi. So let me just share my presentation. Just switching off this video. Sir, it is visible?
Yes, sir. Visible, sir.
Okay. Thank you. Thanks, everyone. So I am going to talk on the characterization of the sustainable materials. So already you have heard about the sustainable materials for the last few days. So today I'm going to talk about the basics of the characterization. So why the characterization is important for the material, why for sustainable materials, and what are the different characterization tools, and what are the basically engineering. This is not basically a single input what we need for that. This is a combination of the many input that will give the overall picture of the materials research. So when for a material science and a materials engineering it is going on, we have to go for a processing, we have to go for a performance, and we have to go for a properties. And all of these three things, they are linked with the structure. So how the structure will behave, basically for the same material, if you can just discuss about, let's say for the steel, that is the material we are using for our everyday life. For the steel is having different structure, and when you go for a different structure, the properties of the steel will vary for that, and based on that, a different performance is coming on that. So as an end user or as a researcher, when you go for that, we need the combine all of these three techniques based on what is our final output or what is for our aim. Based on that, we need to design the material for this. And for that, the structure takes a very important role for that part, and we need to understand what is the structure is coming on that. And more on so, we need to understand the structure, and we need to visualize the structure, because many of the cases what happens that the structures are coming which is basically out of the resolution limit of our eye. So in that case, we need to take the help of the different rules, different instruments, which will make them visible to us, which is otherwise invisible to the human eye. So for this here, I just want to give you a very simple example when you talk about the resolution. So the resolution of our eye, it is something around the 100 micrometer. Okay, so I can just give you an example of this part, that what is an 100 micrometer means. It is basically the width of our hair, or it is a tip of a needle. That is something called the dimension of an 100 micrometer, and with our any unaided eye, we can just see up to this resolution. Anything beyond that, we cannot see this part. Now, when we talk about any of the structure, let's say subatomic structure or atomic structure, when you talk about the nanometer or the picometer, in that level, as you know that when from the micrometer to nanometer, I am just going to give you a simple calculation based on that how much we need to enhance our capabilities. For example, if our 1 micrometer is 10 to the power minus 6 meter, then 100 micrometer which will be there is 10 to the power minus 4. Okay, so for that, this is the resolution of our eye, what we can go for that. Now when you go for the nanometer, let's say 1 nanometer, that is basically 10 to the power minus 9. That means from 10 to the power minus 4 meter to 10 to the power minus 9 meter. So we can see from our eye is only minus 10 to the power minus 4 meter. That is the resolving power of our eye. But from there, when you are going about the atomic resolution, you are going to 10 to the power minus 9 meter. That means 10 to the power 6 times of the increase of the magnification or the capabilities we should need for that, right? There comes the role of all those different tools, all those beautiful tools which will give on that, which will enable us to see from 10 to the power minus 4 from our eye resolution to the 10 to the power minus 9 meter, in that range. Okay, so just imagine the power of that. So if we can go about, if our hair dimension is 10 to the power minus 4 meter and we want to say 10 to the power minus 9, that means if we can take a human hair and we can do like the 10,000 10 to the power 6 meter, it will be around 10 lakhs. So if we can make a division of 10 lakhs of our human hair, then one part we need to see based on this instrument, and that is the power, that is the magnification power, or that is the power of this microscopes having in the present day, right? So this is a very fundamental side, that is basically the combining the material science with theoretical and computation part. So now if we can go for the biological and the experimental part. So the first one, if we can go for that, for our daily routine, how the structures comes for that. So in a metallurgical example, if we can go for that, so let's say this is a car tire. So or any of the tire for that, in that example. So this dimension is something around 1 micrometer. In that dimension we are getting on that, right? So this is the dimension of the tire, we are going for that. Now from there, if you can come out, we can take out the material. Now let's say we just want to know what is the strength of this tire, because we know that this is from the different material that can make on that part, and we need a high strength for this. So then we are coming out something around 10 to the power minus 3, 10 to the power minus 2 of the meter of the dimension. Till that point, we can see with our eyes. Now after that, you want to know the structure, what is the structure is coming in a gross scale. If there is any, what is the grain structure, what is the precipitate, then we want to go for the light optical microscope. So for that, we are coming 10 to the power minus 3 meter to 10 to the power minus 4 meter in that domain. Now from that, even you want to go for further down inside. So in that case, you want to know for 10 to the power minus 5 to 10 to the power minus 4, minus 6, in that range, then you want to go for ACM, scanning electron microscope. This is in the domain of the electron microscope, we are coming from that. So now again, you know that this grain structure, the properties are not dominated by what is the grain and grain boundaries, but there are different sort of the materials defect or crystal defects also come. So these defects are basically a lattice defect that is forming in different cases, like the dislocations you are having, like the twinning you are having, that sort of different sort of lattice defects. So that is coming 10 to the power minus 7 meter in that dimension. And then even if you go much farther, then you can see what is the atomic structure or how the atoms are arranged in that structure. So in that case, 10 to the power minus 9 to 10 to the power minus 12 meter, that is from the nanometer and the picometer domain you are going from that. So that's how we can come down from the top to down approach. We are going from the meter scale to the nanometer scale, but the property in this meter scale, it is basically governed by the properties in the nanometer scale. So that's why we need to understand the structure at different length scale, how it is behaving to optimize the property of the final product or the final of the engineering component. That's why the characterization tools are so important in the research of the material science. So now, just like that, as I told you, this is if called the hierarchy of the materials, if you can think on that. So let me just check that, if I can go for the toolbar. Okay, it is not giving anyways. So this is how the hierarchy of the structure is coming. So if you can go for that, from the macro structure to the mesostructure to the microstructure and to the nanostructure. This is the basic hierarchy of the structure, what you are going from that. So macrostructure means in this structure, what you can see is that the object that can be observed by the unaided eyes, that means the eye resolution. Then if you can come about the mesostructure, that object they are on the borderline of the visibility, that means we can just resolve by our eye, but most of the times we cannot be there, just a borderline. Then come to the microstructure. Microstructure, the object that can be viewed by means of any optical microscopy techniques. The objects, they are the micron size in the 0.001 millimeter. In that size, that is called the microstructure. That is definitely beyond the resolution of our eye. So we need different tools. And then come the structure. They are called the nanostructure. Nanostructure means the object, they have the size between 1 nanometer and the 100 nanometer. Okay. So now, if you can define out the microstructure, as we are dealing in today's talk, so microstructure, they are basically the microscopic description of the individual constituent of a material. So that can be from a 1 micron from the nanometer level. In the most of the modern research, they are basically now talking about not the microstructure, they are even talking about the nanostructure or even the picostructure also. So what does this microstructure, that family, they consist of? They are consisting the crystal structure, the porosity, the size, the composition, the orientation of a material. So how they are relevant for your research? They are relevant because they can do the strength, toughness, ductility, hardness, the corrosion resistance. That is the day-to-day the material property. They are basically getting governed by this microstructural part. Then what are the different methods to go for this microstructure? So first and foremost, the best method is to take a photograph. So normal camera, you are doing it that. If you can see that in the left side image, observe this surface, how this fracture is. So in this fracture, whether this is a brittle fracture or this is a ductile fracture, just by looking the surface, fractured surface, you can determine or you can tell the property of the material. You can tell the metal material or material is the ductile material. Something that if you can go for the optical microscope, then what will happen is that you can say some sort of the different structure, like this is called the Weidmann strata structure. This is basically iron, but the meteoritic iron. So this iron, this is from a part of a meteorite, and from there, what is the structure it is coming, you can understand or you can tell about what is the pressure and what is the temperature this meteorite has experienced in the outer space, or even when it is coming out in the earth space, it is coming out there. So everything has been imprinted, every property or every temperature, every processing condition has been imprinted in the structure, and by analyzing the structure, you can talk about or you can diagnose what are the different conditions they have been experienced on. So how you can go for that? Now, if you can go for a bit beyond, then you have to take the help of the microscopy. So what is the microscopy? Now, if you can just take about the textbook example, that is a sophisticated microstructural examination that involves the higher powered instruments like the optical microscopes, electron microscopes, and so on. Some involving pre-preparation of the material sample like cutting, grinding, polishing, etching, vapor deposition. Probably if the time permits, I will come just one slide on that part. And these methods are overall collectively known as metallography. That is the specimen preparation part. They are known as the metallography part, right? So now the other part is the aspect of the microstructure. If you can think about what are the different microstructural aspects, we can go for that. So first is that the identification of the crystal structure or crystallographic plane in a material. the identification of the morphology, that is the shape, size, morphology, spatial distribution, like that. And third is that the identification or quantification of the materials or the phase chemistry. So there are basically three different rules. So first is that you want to know what is the structure, that is the crystal structure, the crystallographic texture, orientation, the crystal structure. Second is that the shape, size, and morphology, the distribution, like that. And third is that when you understand these two, then what is the materials or the chemistry of that part. So these are the three things when we sit on a microscope or when we characterize any of the structure or any of the material, whatever way it is, be it a biological material or be it metallurgical or material science material samples. These are the three questions you try to answer when you sit in for a microstructural characterization, be whatever way it is. Even for example, even from our eye also. From our eye also, let's say first you see a material, first you just want to know that what is how the material look like for that. Okay, crystallographic part, you cannot do this one until or unless you are having a single crystal silicon and you can see the faceted plane from that part, you can understand from that, otherwise it's not been there. And phase chemistry and quantifications, if it is any chemical solution, then sometime you can go for that, like the smell, like the color from that part, otherwise we have to again go for some sort of the chemical test on that. Similar way, when you go for the microstructure, this also you can go for that. So when you are going for a characterization part, what are the things you are doing is that, so the microstructure, as I told you, so your idea is to get the answer that what are the phases. So microstructure basically consists of the phases and the defects. Phases means same material but different structure they are coming, they are called the phases. And defects mean they are having a lattice defects or a grain boundaries or any precipitate is coming, that is called the defects. So when you sit out the microstructure in an overall set, these are the information you are basically try to look for, and based on this information you just infer what is the other three questions, just what I told you in the previous slide. So the questions what we are asking for that, the type, the distribution, the quantity, the size, the orientation, and the shape. Maybe I will be coming one by one each of them in the coming slides there. So what is the fundamental tenet of the characterization? So first thing is that when there is an interaction between a probe and a material, a scattered signal is produced. We collect and process the signal in the form we can interpret, and then interpretation is the information that we seek, that is the chemistry, morphology, crystal structure. So again, if we try to understand in a simple term, let's say what is a probe called? A probe means it is something like, let's say a probe means something like a spy. So for example, let's say there is a group of people, and if you want to get an information from that group of people, what you can do is that you can send a spy. The spy is disguised as the person of that same group of people, so they cannot distinguish him separately, and he will talk with them, he get the information, comes back and give you the information. Similar thing that a probe does that. So what does a probe is that? Probe can be of the any form. Probe can be if your photon, that is means the light source. Probe can be your electron. Probe can be your ions. All those things can be in the probes, can come from that. So when there is a probe, you can send the probe and send to the material. Inside the material, the probe interact with the material. It will collect all the information from the material. Then the probe comes out from the material, and then you just analyze the probe using different sort of the detectors or the computation part, and then you can get the information of the material, what is happening on that, right? So in this part, if you can go even more fundamental part, let you example on our undergraduate post graduation days, when we are doing for, let's say most of you have done the interference part, Young's double slit experiment. So what you do is that we are putting a light source and you are having a grating. So what it does is that the light source comes, the wavelength of that, it is almost in the order is coming of the light source wavelength in the coming of the grating the lines, and then it interferes from there and it forms a pattern, and from that pattern we can get the information what are the grating periodicities having on that, right? So similar thing here, light is the probe, and then we need to get the information from the grating, and from there we are getting by the interference phenomena, we are getting what is the information coming on that. Similar way, light I am going to give the example, but this is a very broad source. What you can see for that, for most of the modern day characterization tools, we are using electrons or the ions for that part, which can go and which can distinguish the material, and basically they can interact with the crystal structure or the atomic structure, atomic planes of the material, and can come out and give you the information of the atomic structure or the atomic signal. Well, so this is what are the different probes we can use for the entire gamut of the electromagnetic radiation. So first is that the visible light, we all know for that. So based on the visible light, we have done the optical microscopy. If you use the probe as an X-ray, so the X-ray, based on the X-ray techniques, we can go for the X-ray diffraction, X-ray photoelectron spectroscopy, XPS, like that. If you can use the probe as a neutron, then the most popular technique is the neutron diffraction. If you can talk about the ion sources, then the techniques where you can go for that, the secondary ion mass spectroscopy, the ion beam thinning, you can go for that. And then there comes the family of the electrons. If you can use electron as a probe, then again there is a gamut of the families where you are using electron as a probe, and then you can give the information or the materials related information of the different level or different forms. So what are the techniques can use the electron? They are the ACM, that's scanning electron microscope, the transmitted electron microscope, or the TEM, the electron holography, electron diffraction, electron energy loss spectroscopy. There are many techniques has been there, right? So probably in today's thing, we just try to understand the very fundamentals of the part. Maybe one we can talk about the optical microscope, that is the visible light microscopy, and maybe one of the electron microscope, maybe the ACM or the TEM, we can go for that. So let's see how it works on this part. So there are different characterization techniques that are available based on the using this probe. First thing is that if you can go for that, the imaging or the microscopy, if you can go from there. So the imaging part, the optical microscope, the electron microscope, and the scanning probe microscope are coming on this part. Then if you can go for the diffraction techniques. So if you can look for the diffraction techniques, then we are having a X-ray diffraction. We are having an electron. If you can use as a diffraction techniques, then this will be the electron diffraction in the TEM and electron backscatter diffractions in the ACM. You can go for the neutron, then also come the neutron diffraction. Probably the neutron diffraction is very limited in the country. Only in the Bhabha Atomic Research Center we are having a neutrons, simply because for the you need a neutron source, you need a nuclear reactor for that. For most modern days, they are now using a pelletron, but more or less you need a nuclear reactor for that part. Now for spectroscopy, that is essentially will give you the chemical information. So it is you are getting the EDS or the WDS, that is the energy dispersive spectroscopy or the wavelength dispersive spectroscopy. That can be used by the X-rays. You can again go for the electron energy loss spectroscopy, that can be done by the electrons, and so on. Even you can go for the mapping of the electrons or the chemical states. But most important, for getting all this information, there is the different protocol of the specimen preparation. Like your specimen has to be of that order to get the information. So what I told you is that your specimen cannot interact, because your probe has to interact with the specimen. So that means the specimen also needs certain sort of the preparation, so that your probe can penetrate within the specimen, or it can reflect out of the specimen, right? So for the different processes are there. They are called the mechanical grinding and the polishing. We can also go for the chemical polishing or etching. There are the ion bombardment or thinning, the crunching, and different process has been there. So now when we're talking about the different sort of electromagnetic spectrum, so now this is the based on the wavelength. So what is the different electromagnetic spectrum we are going to talk about? So first is that the larger spectrum where you're going to talk about is the radio signal, radio frequency, then come the micro frequency, infrared, like that. They are all in the larger part. Now here you can see the visible light range, right? So it is something around the 4,000 to 8,000 of the angstrom in that value. So this is the only small gamut where our eye can see these things. Our eye cannot see anything beyond of 4,000 to 8,000 angstrom. There we need the tool or different tools or different characters and techniques which can make these invisible things to in our eye level. So for that we need different sort of a detector. Now when we can talk about the microstructure, we are always talking about which is below our eye resolution part, like the ultraviolet, X-ray, gamma ray, and so on. So in this case, as I told you, our electron something coming, it is in between the X-ray and the gamma ray. In that part, our electron is coming on there, the electron sources, and this is the X-ray, that is 10 to the power minus 10 meter. That means again, this can also give you the information. The X-ray also can give you the information for the for imaging in the atomic structure, that is in the picometer or the nanometer level, or even gamma ray can do. But there is a fundamental difficulty, as you know, X-ray or the gamma ray, they are essentially the photons or the chargeless particles. So in that case, what happens is that you cannot distinguish, or you cannot make a electromagnetic lenses. So you cannot bend, you cannot convert or diverge the ray, which is the essential for any of the imaging devices. So that's why electron becomes so popular. Again, I will come there when we will discuss about the electron microscope. So now, again, before we start for that part, I just want to give an idea about what is different unit, what we are using for the characterization part. Already I gave you an example that what is the resolution, like an our human hair is something around 100 micron, that is 10 to the power minus 4 meter, and we are talking about the atomic resolution, that is 10 to the power minus 9 meter or 10 to the power minus 10 meter, in that range. That means it is 10 to the power 6 times of the resolution we have to enhance for that. So if you can talk about the wavelength are in the form of 10 to the power minus 10 meter, that is the angstrom. Now we discuss about nanometer, that is 10 to the power minus 9 meter or 10 angstrom. So this is in the spatial part. And then if you can think about the energy part, that is the electron volt, that is 1.6 to 10 to the power minus 19 joule. In that range we talk about the energy resolution. So we are discussing about this range of the resolution for this part. And to understand or to get the information, what are the different experimental techniques what you can do go for that? We want to go for the microscopy, the spectroscopy, and the diffraction. So now based on that, if you can think about what are the different scattering or diffraction part that comes about. So again, this is a very fundamental physics what we are discussing about. So when any of the particles comes and collide with other particle, what are the phenomena can happen? That will come the scattering. Now scattering and comes of the two different processes, that elastic scattering and the inelastic scattering, right? So what is elastic scattering? In elastic scattering, the energy loss after the collision is very minimum. There is no loss or very minimum loss. And in the inelastic scattering, what happens is that there is some sort of energy loss is coming on that. So that means when any particle collide with another particle, there is some sort of the energy loss is coming on that part. Now, both of these techniques gives us two different sort of the information. The elastic scattering, they basically give you the imaging, or you can image the sample, they can give you the information about the materials, and also they can give you the information of the diffraction or the scattering part. That is the part of the elastic scattering they are giving on that. Whereas the inelastic scattering, what they are giving is that they give you the energy loss spectra, that is the energy absorption, and they also can give you the secondary signal, that is the excitation process that is coming on the energy loss part. Well, so these are the two different parts we are going to discuss about there, and these are two different fundamental phenomena. So now, if you can talk about the elastic scattering, as I told you, they're basically concerned. Now, if you can think about, there is a no loss of energy, then in the energy part, that can give you the imaging part, and then they will also going to give you the diffraction part. So what is the imaging part? They can give you the shape, size, and morphology of the different features of the particles. Whereas the diffraction part, they will give you which angle a particle has got scattered. So by measuring that angle, which can get the information about the crystallographic planes or the characteristics of the characterization of the crystallographic planes or the crystal structure, we can go for that. So by elastic scattering, we can go for imaging and the diffraction. Imaging will give you the shape, size, and morphology of the particle of the materials, and diffraction will give you the crystal structure, defect structure of the material, right? So now, if you can go a bit inside of this, what is the image and the diffraction pattern, if you can look for that. So this is a very fundamental diagram. So if you can consider a light optical lenses, and you can take a object part, this red arrow is an object. So in a back focal plane or in the focal plane, you can get a magnified object, but that object will be an inverted object, right? So this is how a principle, the very basic principle of a lens, in which object as we are getting an image of a magnified image of an object, and so that we can also resolve the part which we cannot see in the real object part, right? This is the very basics of the part. So even our magnifying glass comes with that part. So this is a very fundamental part, and how the magnification is defined. The magnification is defined the size of the image divided by the size of the object, and then if we can do some of our the +2 level of the analysis or the calculations, what we can get it that finally this will come down that the distance from the lens to the object and the distance from the lens to the image, by the ratio of that part, that can also going to give you the magnification part, right? So now, when we talk about the diffraction part, right? So this is the first part, we talk about the basics of the imaging part. Now we talk about the basics of the diffraction part. So what is the diffraction? So in the diffraction means that the bending of the light, right? So we are having a parallel beam of light is coming on that, and then we are having light this type of an object where there is a very fine slit comes on that. So what will happen is that in that part, light will start bending from there, right? So now, if you can consider light as a particle, you cannot explain this bending of this part. Rather, if you can consider now light as a wave particle, then wave particle duality, what you can think is that after coming there, the wave start propagating there, and now the wave will start propagating. They will try to interfere among themselves, and they will make a pattern. So in a screen, you can get that there is a very bright pattern in the center, and then having the first maxima, second maxima, like that. So it will be like this type of the ring pattern you will be getting in the screen. So this is nothing but the diffraction pattern what you are getting from that. Now by measuring the spacing between these rings, you can get the information what is the spacing between this slit of the object you are getting from that part, right? So this is the fundamental of the diffraction. So we just come to know what is the fundamental of the imaging and what are the information that can give it to you, and then what is the fundamental of a diffraction and what is the information they can give it to you. So just now what I told you, the same thing is only mentioned there, that the parallel light rays which pass through a small aperture, they begin to diverge and interfere with one another, and this becomes more significant as the size of the aperture decreases relative to the wavelength of the light passing through, but occurs to some extent for any size of the aperture, exactly what I told you there. And since the divergence rays now travel at different distances, some move out of the phase and begin to interfere to each other. So there is a phase difference between the light, as there is a path difference comes on that, and that comes the interference part, and based on the interference pattern, you can get the information of what are the object properties there. Exactly, again I'm telling you that part. So this is the interference pattern, and by analyzing this interference pattern, or this is basically the 1D view of this structure. So by analyzing this interference or diffraction pattern, what you can get is that you can get the information of the object there, right? So far so good. So now from this diffraction, they are basically governing the resolution part. So any of the characterization equipment or characterization instrument you can talk about, like the optical microscope. Let's for example optical microscope itself. So what determine the resolution of that part, right? So just now I just introduced you with that pattern. They are basically called the airy disk. So this is a diffraction pattern, the very simple diffraction pattern. Let's say a light source is coming out there, and you are having an object which is having a single hole, and then we are getting a pattern in the image plane. So this pattern you are getting. So now in the 3-dimension, basically this is a 2-dimensional pattern. In a 3-dimension, if you can look for that, in 3-dimensional, this will be a pattern like that. So in the center, there is a Gaussian peak, and then there comes all the first maxima, second maxima, like that. So now let's say you are having two nearby sources, one source near to the other one, right? And in that case, what will happen is that both of these sources will give you one of its properties, like this are the airy disk or the airy pattern they are giving it to you. Now when these two patterns they are coming near to each other, then what will happen is that the gap between these two, if this is coming within the 80% of the main peak, then you can resolve them. If you cannot, if the gap does not come 80% with this part, then you cannot resolve this part. So that is called the Rayleigh criteria. So what Rayleigh criteria is like that, exactly what I'm trying to say you. So let's say you are having two nearby points, and you want to resolve, you want to see these two nearby points distinctively. So one nearby point, this is how the point will behave in a diffraction plane. Now if you are having 2 points, now this is one first point and second point. So both of that point, they are going to give you their own characteristic disk, airy disk. Now you try to bring this 2 point, this point 1 and point 2 come closing together. Then what will happen? After a certain time, what will happen? These 2 points will coming together, and then they will merge together. At this point, we cannot see these things. So the point exactly at which we cannot distinguish these 2 points as a single point, these 2 points as 2 separate points, that is the limit of the resolution we are getting. So how close we can bring these 2 points together? So there is a formula, they call that the gap between this part. So when there's overlap there, the gap between this top to this overlapping point, that should be 20% of the entire height of this airy disk, of this first maximum of the airy disk. Then you can resolve this 2 points as 2 separate distinct points there, right? So this is how the resolution point has been defined. So now let's see for this. So now saying that from the concept, now let us come out a bit complex part. So what we are coming on that? We are coming on an optical microscope. So in optical microscope, exactly what I showed you there. Now instead of in 1 point, now you are having 2 points. This is the point 1 and the point 2, and the distance between these 2 points is the delta. So now you want to distinguish this delta, or you want to say this 2 point as a separate point in the image. So how we can go for that? The image has been formed, there is the lens has been there, and then finally we are getting the intensity has been forming there. So if you can do a numerical calculations, then the resolution, that is basically the distance separation, how they will be related is that 0.612 lambda by nu sin alpha. forget about 0.612 lambda, you just make it that this is a constant part. So what are the part it depends? It depends on the lambda, it depends on the mu, and it depends on the alpha. I am coming one by one. What this are for? This lambda, this is nothing but the wavelength of the light wavelength you are doing from that. Now this mu is nothing but this is basically the refractive index of the medium in which light is passing through. And sine alpha is basically the alpha is the semi aperture, the aperture of that size of the aperture of your lens size, and this is the sine alpha is the sine function of that part. Now if you can consider this, what is the maximum alpha? So now here you can see that if you want to increase the resolution, then you have to either decrease your lambda, because directly proportional, you have to decrease your lambda or increase this part, right? Then only your R will come down. So now we will come lambda a bit later. Now let us first consider this part, sine alpha. So whatever be the aperture, what is the maximum value of sine alpha? Maximum it can go to 1, right? It cannot cross 1. So sine alpha has been 1 means maximum we can consider as 1. So mu also there is a limitation. Let's say maximum what you can do is that most of the optical microscope, they are either coming in the air or the air medium. There we are having basically refractive index as 1, or maximum you can put the lens system into an oil immersion lens. There we are having 1.2 to 1.3. That's also it has been fixed. So what basically determining the resolution of a microscope, optical microscope, is comes the lambda. So now there also how much you can vary. As I told you that the resolution or the light optical wavelength that varies from the 4000 angstrom to the 8000 angstrom, right? So if you want to go for that maximum resolution, what you can achieve is like that. If you want to use a violet light that is with the 4000 of the angstrom, you can go for that part, right? So maximum you can go for this. So then this comes is that in a light optical microscope, you cannot go beyond a certain point because of your light wavelength or the optical wavelength. So this determines that this fix the resolution of a light optical microscope, normal optical microscope. So now if you can go make a small calculation. So just now what I told you that improve the resolving power means that reduce the delta, that is the spacing between these 2 points. So reduce the delta for a better optical microscope is that, okay, you can always say that you can go for the UV light or the X-ray, but then you cannot go for the absorption problem, you can go for the lens problem. You cannot make the X-ray lenses because the particles are chargeless particles. So you can have to increase the refractive index. So maximum you can go for the oil medium instead of the air medium, but in that case you can also cannot increase maximum 1 to 1.2, you can go for that. So this is a small chart what you can go for that part. So in this optical microscope, in the resolution, if you can put in the air medium and the oil medium, and you can consider about the red light to the violet light. So red is 650 nanometer and violet is 400 nanometer. So maximum you can use the microscope, you can make an optical microscope using a violet light with an oil medium, and there also you cannot resolve beyond 0.17 micrometer, right? So you can go to 0.17 micrometer or 0.17 micrometer, and in that level you cannot go to the nanometer level or the sub-angstrom level, you cannot go for that. So using an optical microscope, whatever you do, you cannot go to an atomic structure resolution, you cannot resolve the atomic structure, you cannot see the crystal structure of a system, right? You cannot see a grain of a system, you cannot see the defect of a system, right? Or even in the biological samples also, if you can think about, you cannot see the DNAs or the RNAs or the cell of a system in an optical microscope. So what is the way out for that? So way out is that then you have to reduce the lambda. So you have to reduce the lambda means then you have to leave from the gamut of the light optical microscope, and then you have to come to the family of the electron microscope or subatomic the wavelength the particles where the wavelength is less than electron part, right? So well, before going into the electron part, I am just going to introduce a bit about the contrast part, because this is also very important. Contrast means it is not only important to understand the microscope to resolve the two nearby particles, but also the contrast also should be the different. There should be some different contrast should be there. So what is the contrast? If you can talk about the basic understanding of an contrast like that. So contrast means in a white background, let's say you're putting a white object. Can you see, even though if your microscope can resolve, or your eye can, for example, let's say take the eye. Let's say you can take 2 white points and which your eye can distinguish very clearly. But then if your background become the white also, they cannot see like that. For example, even in this PPT, let's say when you're talking about, so all in the white background, I am having the black letters, right? So now if you can pick my background also black and the letters are also black, so in that case, what will happen? Even though I can read the letters, but as the background is also black, my contrast is getting lost. So in a mathematical way, how we can distinguish the contrast? So it is basically the intensity which is coming by the specimen minus the intensity is coming by the background and averaged out with the background intensity. So that means the difference between the intensity of the specimen and the background will be as much our contrast will improve from there. So this is again one example. I'm just going to give it to you. So let's say in this background you are having a same object but with different contrast. Here inside the box, the color inside the box, the gray color, this is basically grayscale image. The color inside the box, inside and outside, they're almost the same. So if you do not have this black boundary, you cannot distinguish the inside and the outside part. And if you can start slowly increasing this part, and then if you can coming on that, you can see it here in the 50% contrast. At least even if you do not have this black boundaries, you can distinguish the white part and the outer scale part. So why the contrast is so important is that our human eye, we are having some limitation. So even though the microscope can give you the better images, but better resolved images, but finally at our eye, which can see the microscope images, right? Now for our eye, we are having a contrast of the 0.5 to 5%. Based on observation, what I can go for that. So 100% contrast, the difference between the pure black and the pure white, that is a 100% contrast. But most of the cases, we are not getting 100% contrast. We are getting somewhere in between the contrast, between the 5% to 80% the contrast, what we are getting in most of the cases there, right? So now come out the fundamental of the electron microscope. So before I coming to the electron microscope, what is the difference is coming on the electron microscope? Let's see on that. So you can think of some fundamental examples for like that. Let's do some thought experiment, right? So you just think about, you are having a frame, and in that frame you are having different balls, and you are putting a light source in the top of that frame, right? So in the bottom, what will happen is that you are going to have some sort of a shadow. So that's exactly, and the shadows will come up, all the balls will give the equal shadow. So now what you do is that instead of doing the things, now instead of all the balls, now what you will do is that you put all the balls of the different materials. Let's you take that one ball made, let's say made of copper, one ball of iron, one ball of the wood, let's say one ball of the glass. A similar way you can put different materials, and then again you put the light source from the top of that. Again in the screen or in the ground, what you can see on that, you can get the image, the shadow. So again, by looking in the shadow, you cannot distinguish what ball is of what. You cannot distinguish that, okay, this shadow is coming from the iron balls, or this shadow is coming from the copper balls, or this shadow is coming from the wood. Now you keep the same frame together, and instead of the light source, you put an electron source in the top, and somehow let's all the balls, they become the electron transparent. Then what will happen is that when electron comes through, and then finally again when you get the image there, the image will be different for the different of the balls. So the image which is coming from the iron balls, that will be different for the copper balls, for the aluminum balls, or from the wood in that sense. So why it is like that? Because electron, they not only make the image by the shadow formation, but electron can pass through the material. They will interact with the material in a quantum mechanical way. I am not going to cover up all those things, but that is much more fundamental part. Electron comes out with a quantum mechanical way, interacts with that, and then they forms the image in the background. So when you go for the electron microscope, very basic. So first we try to get the answer that why you need the electron. What do you do with the electrons, electron microscopes? Then different sort of lenses like the electrostatic lenses, electromagnetic lenses, then the electron matter interactions, and the different electron source, and the very basic operation of the ACM on the TM if the time permits for that. So this is a very fundamental subject, or the historical development of the electron microscope. So as you know that the first electron microscope, the electron has founded or discovered by the Thomson experiment in 1897. They first discovered the electrons, and they just told that electrons are charged particles. And in 1925, the de Broglie, they just founded the quantum mechanical rule, and they told that electron is not only a particle, they are basically wave particle duality comes on that. And then in 1927, they go for the diffraction experiment. And then finally in 1930s, the electron microscope, they have been discovered, the Ruska and the Knoll, and for that they got the Nobel Award in 1986. And from the electron microscope, this is how the resolution comes. So this is our human eye. This can see from this length to this length, let's say 1 meter to 1 millimeter, or the razor blade, what I told you, give the example, that is 100 micrometer. That is the human eye, we can see with that. Now, if we need to see anything beyond that part, we need a light optical microscope from 100 micrometers to the 0.17 or 0.1 micrometer. Just now we saw that. So what comes on that part? Till the most of the cells, the bacteria, we can see with the light microscope. Now, from electron microscope, if you need to see on that part, so from 0.1 micrometer, that is 100 nanometer, to the sub-angstrom or angstrom level or picometer level, there we can see the electron microscope. So there what you can see is that we can see the viruses, the different molecules, the atom, that we can see from the electron microscope, right? So now the question comes that why electrons? Now the question comes that why electrons, you go for that. So as just now I told you that electron we needed that because electron can give you much more finer wavelength. Light optical microscope, there is a limitation of the light wavelength. So you cannot go beyond of the 400 nanometer of the wavelength. So if you need to distinguish any particles which is having I am audible, right? Still?
Yes, sir. Yes, audible, sir.
Okay, thank you. Thanks. So now you go for that part, why the electrons is coming on that. I am not going to the details of the mathematics there, but as we talk about the wavelength of the electron, so what is the wavelength we are going to talk about? So in an electron wavelength, when you're going to talk is about is that this is something around, let's say at 30 kV, the acceleration voltage, if you can go for that, electrons are having something around the 0.0027 nanometer at the 200 kV and the 30 kV 0.007 nanometer. So this is the wavelength range when you're going to talk about. So this is a very basic calculation, the basic fundamental of the de Broglie wavelength. We can go for that, we can determine the electron wavelength there for the charge particle duality. So this is the wavelength we are going to talk it about. So now, if you are having a wavelength of the 0.007 nanometer, that means the 0.07 of the angstrom, then that is basically we are coming to the atomic resolution and atomic domain, and that's why electrons can give the information of the atomic structure. So this is the list, table what has been available in the open literature, that what is the, if you can increase the accelerating voltage, then how the wavelength will be vary from that part. So at 100 kV, 120 kV. So as you know that when you discuss about the electron microscope, be it the ACM or the TEM, they are running at a different accelerating voltages. So at every voltages, the wavelength also getting varies. That means as we increase the accelerating voltage, what will happen is that the wavelength is getting much more finer and finer. But we have to take it a pinch of salt that even though the wavelength is getting much more finer and finer, but what is happening is that the irradiation damage, the electron damage or the irradiation damage also get increased. So material will getting damaged also. So if you are having a fine biological sample, let's say you are working on a tissue or you are working on a cell or the viruses, in that case, if you can go for a higher wavelength, then they will damage the system. Even in material science also, let's say if you are working on a carbon nanotube, let's say you are working on a 2D materials, layered materials, you are working on energy materials, let's say on a battery materials, lithium ion batteries, you are working on that. But there also what will happen is that you are going for a higher accelerating voltages, they will make some beam damage or material damage. So that's how in a modern day microscope, what people they are looking for that, they are basically looking for the low accelerating voltages. But even though the wavelength is low, but then they are going for aberration corrected lenses. That is again not, we'll not going to cover in this lecture, but I just give you the information that is the most modern research of the electron microscope, they are going on that. So this image, I can skip on that, just now I discuss on that part, but I just point out one small thing. So you have seen the X-ray and the gamma rays, and this is exactly the location where the electromagnetic waves or electromagnetic rays, they comes from that part in the gamut. So this is our visible light, and from there we are going to get the information of this wavelength. So that means 10 to the power minus 6 to 10 to the power minus 7. In that particle size range, we can see from our eyes, and from there, what we are going from that part, we are going to see that 10 to the power minus 12 to minus 13 in that wavelength range, we are going to get the information. That means the materials characterization for technique will give you the information from this level to this level with different sort of the tools, with different sort of the parts, which is beyond the resolution point of our eyes. That means that in human race or human civilization, we are developing the techniques from where we can get the information of the entire electromagnetic ranges. I'm not going to talk about the higher ranges because, as you know, already the techniques have been available where you can go for infrared imaging, microwave, or the other parts. So now, if you can discuss about continuing why electrons. So what are the electron positive points are there? The first thing is definitely, as you know, that electrons are having very fine wavelength. So that means they can go and interact with the materials from the crystal structure. Second thing is that electron is having the particle behavior as well as electron is also having a wave behavior, wave nature of the electrons. So that means electron can give you the diffraction information also. So when you are considering electrons as in particles, electrons can give you the images of the material of any of the characterization, and when you discuss about electron as in wave, electron can give you the crystal structure or diffraction information. Another part is that electron is a charged particles. Charged particle means you can design the electromagnetic lenses. That means like in optical lenses, you can have a light and you can put a light lens, so the light will get bent, right? But electron cannot interact with the glass lens. So for that, you need to design different set of lenses. They are called the electromagnetic lenses. So there, if you can apply different set of the charges, and with this charge field, electron will bend. They will either converge in the system in that part. So I'm just summarizing out for this part why you are getting for electron microscope. So the same thing, the negative charge you are getting from there. Electron is a low mass. It is having a dual behavior electron. That means wave and particle. So what the wave behavior can give you? So even it is a base fundamental physics, but wave behavior will give you the elastic scattering that basically give you the images. It can give you the crystallographic information, and it can give you the higher resolution. The particle behavior means it can give you the inelastic scattering. That means you can get the chemical information. So electron microscope can give you the spatial information and the crystal and the chemical information, all the things together. But for that, what you need is that you need a strong electron matter interaction. That is extremely essential. And for that, you need the good vacuum and the very thin specimen. So I'm going to come about that the electron matter interaction slowly. So when you need the electron microscope, so again I told you that part. So electron microscope means which is beyond the limitation of the light optical microscopes. That means that's 0.2 micrometer as the limit. So if you need any structural features, any microstructural features that is beyond the 0.2 micrometer, for that you need the electron microscope. We have to go for the TEM or we have to go for the ACM. So this is a bit history of the ACM. So first ACM was developed in the 1942 and commercially they come available in 1965. So what has been late because we are having a scanning tool need to develop for the ACM from this part. We can just skip this one. So what it can give you the electron microscope? So electron microscope can give you the crystallographic information. So what is the different structure? From crystallographic information, what are the information you can get it there? You can get the conductivity, you can get the electrical properties, you can get the strength of the material, everything you can correlate with that. You can get the morphology. Morphology means how the particles shape, size and behavior they're going from that. So from this morphological part, you can get the ductility of the particle, you can get the strength of the particle, you can get the reactivity of the particle. You can get the topography. Topography means how the electron looks in your material looks in 3 dimension. So like you can get the hardness of the system, you can get the reflectivity of the system. Then you can get the composition, you can get the information of the composition of the material. So from what does that mean? That by knowing the composition, you can get what is the melting point of your system, what is the reactivity of your system, what is the hardness of your system from this. For example, like let's say in an additive manufactured material, when you are discussing is about in additive manufactured material, you know that the same material when you go for additive manufacturing there, same material you can also go from the melting route and also you can go for additive manufacturing route. That is essentially a powder metallurgical route, and then you are doing the laser bed melting for making that particular complex structure of this additive manufacturer's component, right? But the problem is that the same material, if we can when you go for the conventional melting and the casting route, and the same material you can go for additive manufacture route, sometimes the behavior is not become the same simply because of the structural part. And at that point, if you can look the structure, like let's say the ductility strength, if you can think about the mechanical behavior of the material, so the ductility strength of this part, then if you can do the structural characterization, you can find that the microstructural features of the additive manufactured component and the same component, if you can make it by the casting route, will not be the same. Then you have to go for the materials engineering, metallurgical engineering to bring these two things in the microstructurally similar part. Similar way, the hardness also behave in the same thing. Similar way, the melting point also go for same things, right? So that's how I'm saying that the microstructure is getting so important, even though the same information we are getting there, but this all the information they are greatly developed or greatly depends governed by the microstructure part on that part, and also you can control the microstructure or you can design the microstructure to fine tune this particular property like crystal information, morphology, topography, composition, all those things. So far so good. So let us come about the very basics of the electron microscope. This is in general electron microscope comes out, but believe me, this is a very simplified structure or simplified model of electron microscope. So what is there? We are having electron beam, we are having a specimen, The electron comes on the specimen, interact with the specimen, different set of the information is coming from the specimen. Then we are having a different lens system, and all the lens system finally they comes out. They are having a plane. Either we can allow them to diffract or we make the images. So in this case, I am just showing you the single lens. But in a modern day electron microscope aberration corrected TEM, there's something around 27 lenses are there. So that 27 lenses coming system become extremely complex from their part. But even though that is the complexity, I'm not going to the engineering complexity of that part. Rather, this is a very fundamental part of what are the different lens system they're coming on these things. So we are having an electron, they falls on the material or the specimen, it interacts with the specimen. As very beginning, as I told you, the concept of the probe. So electrons are works as a probe. The probes are going inside the specimen. They interact with the atoms, crystal structure, grain boundaries, everything. They comes out with that, get all the information. Then they are getting magnified with this lens system, and finally they comes out from the image. And that image you are analyzing with different detectors, computers, and get the information of the materials, what are the structure it has been there. That is the very basic of the electron microscope, how it works. Now, this part is very important. So when an electron interacts with the material, what are the different signals it comes out, or what does these different signals will tells to you, right? So based on that, what are the different signal is coming out? Now, based on what information you need for the material, you can design your experiment in such a way. So when an electron interacts with a material, what are the different signals? So now let's say this dark one is a specimen. So many electrons can also pass through the specimen and many will reflect out. So first think just about when the pass through, what are the things you are getting? You are getting the most of the electrons will pass through from there, and you are getting the diffracted electron. So diffraction event is coming there. So this diffracted electron, they will going to give you the crystal structure of that material. So again, I'm going to talk about, let's say you are talking about the steel part, and let's say you are talking about additive manufacture, steel component, and the casting route. If you are doing something like that, so that depends that you are having a ferrite phase or austenite phase. So the material, the property of the steel will be different when it is in the ferrite phase, and the property of the steel will be different in austenite phase. So how to distinguish? A ferrite structure is basically a BCC structure, and austenite phase is basically a FCC structure. So now if we can go for a diffraction analysis, understand this is a BCC structure, that body centered cubic, or the face centered cubic, will understand which phase it is there. And let's say you need for a high strength steel, then you have to go for a ferrite structure. Then you can always do some microstructural engineering to convert this austenite structure to ferrite structure. But before that, you need to know that which structure it is there. So this diffraction will tell you there. And then also you are having some of the absorbed electrons that also give the chemical information. Now let's come about the reflected part. What the reflected signals they're coming on that? So you are having a OJ electrons, you are having a secondary electrons, we are having a backscatter electrons, we are having an X-ray, we are having a Bremsstrahlung, we are having the fluorescence, that is basically the visible light and the heat. So it generates the visible light and heat also. For the timing, we are not going to consider anything about the visible light and heat. We consider they are basically make the noise. But then these are very important. So the OJ electron, secondary electron, backscatter electrons, and this X-ray. So this Bremsstrahlung is also one sort of X-ray, but this is a continuous X-ray, not the characteristic X-ray. So what does this give you? That the OJ electron is coming from the very basics of that part, and they are going to give you the valence state. What is the valence state of the electron? What is the oxidation state of the electron? So as for today's course, it is out of the scope, so I'm not going to discuss much about the OJ electron part, but just to know that what information it can give you, that it can give you the oxidation state, valence state of the system. So now it comes the secondary electron, the backscatter electron, and the X-ray. So these two secondary electrons and backscatter electrons will give you the image information, how the materials look like, what the grain structure look like there, and X-ray will give you the chemical information of what are the chemistry present in the system. So based on that, if you can do on that part, this is basically how electron matter interaction volume will look like that. So the OJ electron, they are coming from the very top surface of the layer. They are coming from the 10 angstrom of the surface layer. So they are very surface sensitive tool or surface sensitive information going to give it to you. Then comes the secondary electron. Secondary electron means when the electron microscope electron source comes from the material and then it interacts with the material and the electrons will comes out. They are called the secondary electron. Then below that, this is coming from the 5 to 550 nanometer, that is the 50 to 500 angstrom of the layer. Then below that, it comes the backscatter electrons. So what the backscatter electrons? They are essentially the electrons which is interacted by the material nucleus. So nucleus means as the nucleus is the proton and the neutron, they are basically a heavier masses within the atom structure, and from there it can go for a Rutherford scattering, and directly it will come out from the material from there, right? So that is from the backscatter electrons, and then it comes the X-ray or the characteristic X-ray that can give you the chemical information part. So now you can go about the secondary electron. They are basically the incidence electron. They are passing near to an atom in the specimen. So they are near enough to impart some of the energy to a lower energy level, usually the KSL electron, and they cause a slight energy loss and then path change in the incident part. And ionization of the electron comes about. So when an electron comes near to the materials, it interacts with the atomic electrons, and with the interaction, atomic electrons will come out from the system, and they comes out of the secondary electron part. Similar way, if you can go about the backscatter electrons, as I told you, when the electron comes, they comes near to the nucleus, and from the nucleus it undergo the full backscattering and Rutherford scattering, and they comes out from the system from there. So as it is coming near to the nucleus, so what will happen is that it can also contain some sort of the Z information, the nuclear information. So in a ACM, ACM is a secondary electron microscope that can give you the signal both the secondary electron and the backscatter electrons, and you need to decide as an user of the ACM that for what information you needed that, and for that you need to go for the secondary electron or the backscatter electrons. So as I told you, secondary electrons is coming from the top surface of the material, so it is very good for doing the shape, size and morphology of the system. But backscatter electrons is coming from the nuclear part. It may not give you that much crystal clear image of a material shape, size and morphology, but that will give you the Z information, the atomic number information that is going to give it to you. So when you go for this part, this is very basics of the ACM, how it works on that. So again, the ACM system, we are having electron source, then we are having a condenser unit, we are having a scanning unit and objective lenses. So from there, electrons comes from there. It is getting in the condenser lenses. From there, it is going from there, and then finally it is come from the detector, and then it is coming on this part. This is the specimen. Finally, it's coming on the specimen here. From the specimen, different sort of the detector getting generated, the AC, the BSC, the X-ray, and they are getting on the detector part. Well, I mean, I'm not going to skip this part. This is, I mean, even you can come out from there. So let's come on the most fundamental part there. So in this part, what we're going to give it to you is that in this lens, in the ACM, we are not having many of the objective lenses, but where we're having a set of the condenser lenses which condense your beam and then finally falls on your sample. And when the electron beam falls on the sample, different set of the information it comes out, and they're going to the detector part. So I'm just going to I'm going to skip this thing. I'll come to this part with an example later part. So this is how a ACM image will look like that. So in this case, the many distinct point of the various grayscale that add up into on the viewable images. So when you get an ACM image, first thing we just look about. So what is the length scale you are getting? That is 5 micrometer. That means you are getting a 5 micrometer length scale. That means you are getting an information that is beyond 0.1 or 0.2 of the micrometer level or beyond from that. Is the first thing. Second thing, you can very clearly see this different tiny features, right? So by the way, this is the feature from a ceramics, from a ceramic materials, fiber EM for ceramics from there. And here you can see the top part, and you can distinguish every individual line or every individual fiber from here. So this is basically AC image. So now when you go for an AC image, when you go for the electromagnetic lenses, two different things you need to distinguish. The lens error comes to your part. That is, one is called the spherical aberration, one is called the astigmatism. I'm just going to talk about astigmatism. This is a very basic part when we just clear about. So astigmatism means a spherical part should look, spherical features should look like a spherical only, and it should not look an elliptical part. If it looks like elliptical, that means there is an astigmatism comes on that. This is comes with the, as you are using the electromagnetic lenses, this is the disbalance between the electromagnetic charges between the electromagnetic lenses. So there are different lens calls with which you can correct this particular part of the astigmatism things. So why I'm saying this thing? So this is the important part in a ACM when you are sitting in the ACM. So two things you have to go for that. You have to look for the focus, and you have to look for the astigmatism part. So then you are going to get a very good image in a ACM. So in this image, if you can show for that, in the central image there, the central image, this is not a focused image, but astigmatism is corrected. If the astigmatism is bad, you can see this here, the features look like an elliptical part, that means it's having a bad astigmatism. And if it is a circular feature is looking like a circular, then there is no astigmatism comes in the picture. And then you can come to a focus. Then what will happen is this is the best image you are getting there. So here the particles are also in focus and there is no astigmatism also there, right? So again, we already discussed this part. What is the electron matter interaction? So yeah, this is the part I'm going to talk it about. So what is the difference between the AC and the BSC image? So now you know the different sources, how the AC is getting generated into the system and also how the BSC is getting generated into the system. AC is your secondary electrons and BSC is backscatter electrons. Now look the first part. So in this part, this is again basically a steel sample. From there you are getting synthesis to a powder metallurgical route. So here you can see that you can see different particles. Let's say here one feature is coming there and there one feature is coming there. You can very clearly see the different features and also you can distinguish between which feature is up and which feature is down. That is called the depth of field. Just now I told you before some slide back that I come with an example. So depth of field means in ACM is a very good tool which can focus two different objects at a different height. That means it is having a very good depth of field and depth of focus, which essentially is not been there in optical microscope. Okay, by saying that, now in AC image, what can give it to you that it can give you the very good safe size and morphology. Now come to the BSC image. In BSC image, now if you can compare, let's compare. This is the same, by the way, the same part of the specimen of the image. So now just look this left light edges. And here are the edges. In the AC image, the edges are much more sharper. Here it is not that much. It's a bit blunt. But what you are seeing it here, here you can see some sort of contrast. You can see that this particle is brighter than this part, and this part is brighter than this part, right? So what BSC image can tell you is that it can give you the direct information from the atomic nucleus. It can tell you that the atomic number for this component is more than this, and this atomic number is more than this. So let's say in your system you are having three different features. Let's say you are having a system in a steel matrix. You are having some aluminum precipitate you are having on that part, and then you are having some titanium precipitate. Based on that, now in the atomic number of the steel matrix, the aluminum and the titanium, they are in the different. So in the BSC image, both the things will be comes as a different way. So the contrast you are getting from the aluminum will be different from the steel, from the titanium. By the way, just to keep it in mind is that the high Z or for the element for which the Z will be higher atomic number, the scattering will be more. That means more number of the backscatter electrons will generate. So that will appear brighter. And the low Z atomic number, from there the scattering is less. So less number of BSC or backscatter electrons will generate. So that will appear darker into the system. So just by looking that in this part, you can say that the atomic number for this background is less. The atomic number of this part, this feature is the maximum, and then the atomic number of this part is somewhere in between of that, right? So this is the distinction between the AC and the BSC image that can give it to you. And side by side, if you can go for a BSC and the AC, that will give you this information. So now you know that. So again, let's say again, if you are coming for again, you are in a sustainable material. Let's say if you are working on the additive manufactured material itself, and you are having a different sort of the precipitate, and you want to understand that what are the different Z number or different precipitate is varying and different Z number varying is there. Let's say in that component you suspect that you are having a precipitate from the two different material. Let's say, just example as I give you, let's say you are having some titanium carbides and you are having some chromium carbides. So then if you can do a BSC imaging, it can very clearly distinguish in a steel matrix how the chromium carbide will look like, how the titanium carbide will look like, right? So far so good. So now if you can go about how the resolution in the ACM looks like there. So as I told you that in a ACM the signals comes in a form of a sphere shape volume. So how close these volumes are coming together, that basically distinguishes the resolution of a ACM. So in this case, the resolution, it can be resolved the two nearby point, but in the other case, it cannot be resolved from this part. So for that, what you are going for that, as you decrease the kV, making the kV lower, let's say in a ACM you are working on a 30 kV or the ACM you are working on a 5 kV or the 1 kV, the volume will reduce. So now just the previous slide, you see that if the volume is low volume, then resolution will be better. And if the volume is maximum, then the resolution will be less, right? So from here, you can see that if you want to go for very high resolution, then you want to go for the lower kV, so that the interaction volume will be coming lower and the lower. So this is again one example. This is a biological sample. In this sample, if you can go for that, so this image has been grabbed at the 5 kV and this image has been grabbed at the 15 kV. So here you can see for that in the 5 kV image is much more clear and the resolution is much more better than the image that has been grabbed at the 5 kV. So similar example, this is from a metallurgical sample. So again, this is 1 kV, 5 kV and the 20 kV. Here also you can see this one. The features are much more brighter in the 1 kV and the 5 kV than the 20 kV. So if you want to go for a very high resolution imaging, you need to go for the lower volume. And this is how the resolution depends again on the Z, the atomic number. If you are having a lower Z, again the interaction volume will be more, and the higher Z it will be less. So in your material, you are having a low Z element or lower atomic number element. If you suspect there, then you definitely have to go for a low kV. For a high Z, doesn't matter because the interaction volume itself is low for a high Z system. So I'll just skip this part. So now what are the things you can do with a modern ACM, right? So this is a ACM what we are having in our lab in IG card. This is done by the Thermo Fisher Scientific, that is called the Nano Lab 600i. So it is having a resolution of 0.8 nanometer. It can go for that. It's not 0.8 nanometer. It is a 8 nanometer, not a 0.8 nanometer. It's a 8 nanometer. It can have several monochromators. It is having different pole pieces, superior lens design. It can do the EDS, that is energy dispersive spectroscopy. It can give you different texture sort of information. I'm not going into this part. So by doing that, let us introduce the energy dispersive spectroscopy. This is the last section. Probably we are going to cover it today. So far we are discussing about the energy part, right? Imaging part. Now ACM can also give you the chemical information that is come with the inelastic scattering. So that is come with the X-ray diffraction spectroscopy or the X-ray part. So what can give is that? So X-ray can give you the identification of the element. It can give you the quantitative analysis of the element and the mapping element. So if you can ask about what are the element presence, how much they are present and where they are present. So these are the three answers you can get from there, right? So this is a very basic of the X-ray generation. Probably all of you know this part, but I just make a refreshing part. So when an electron comes out from an outer electron comes and it interacts with any of the core shell electron in atomic structure, let's say 1s, 2s like that. So it just knocks off one electron from there. So if there is an electron knocks off from there, atom do not like any vacancy in the core shell electron. So what will happen is that from any of the higher shell electron, they will jump out to occupy this vacant position, and the energy difference between this higher shell electron and the lower shell electrons, that comes out as an X-ray from the system. That's all. So this is how the X-ray is getting generated. So now when this happens is that the X-rays comes out, that comes of the X-ray part, and if it not getting comes out and it is getting absorbed by any of the valence shell electrons, outer shell electrons, and then that electron will comes out, then there comes a OJ electron. So this is a very basic principle, and all of you know these things. So by doing that, this is again the same thing in a broader sense, that different with different atomic level energy splitting we consider this part, but again the fundamental same only. So if you are having a vacancy in the lower level, let's say K cell electron, and one electron is coming from the L cell or the M cell, what will happen is that they will jump from this higher cell to the lower cell, and the energy difference between the higher cell to lower cell, they will come out from the X-ray. Now for every element, they are having a distinct atomic arrangement, and the energy difference between the L cell to K cell or the M cell to K cell, they are different. So just by measuring this energy difference, the X-ray will come out. So let's say for an element A, when the X-ray will jump from the L cell to K cell, let's say this energy is EA, and for an element B, when the X-ray jumps out from the L cell to K cell, the energy is the EB. Then by measuring the X-ray energy EA or UB, you know that what element it is from. It is coming from element A or element B, right? So this is the very, very fundamental principle how the X-ray spectroscopy works in a ACM. So, but now how it works? So this is basically the in a ACM configuration. This is where all the detectors come from there. So all the electrons comes, it falls on the sample. In the sample, when electron interact, different sort of the interaction, different sort of the signal generated from there, and then these detectors have been placed on that, and the signals going to the detector, and they are getting distinguished from their part. So what there are different type of X-ray, as I told you. First, the characteristic X-ray. So exactly that L alpha or K alpha, just now what I'm talking it about. So this is basically from the L cell to K cell, what is coming on that. They are jumping on this part. Sorry, so L to K is K alpha, then M to L is the L alpha, like that they're coming on that part. So we are having a characteristic X-ray, and there always comes a background X-ray. So that is basically a noise. They are called the continuum X-ray, or sometimes the Bremsstrahlung. So we are normally not considering those things. And in fact, the modern microscope, the software itself has been designed in such a way that they will take out they will take out the part from this modern part, right? So in X-ray, when you go for the EDS, they are having a different of the issue, the having a generation issues and they are having a detection issues. So how they are getting generated? So now let's say the X-ray is getting generated into the system, and from there it goes from a detector. Now detector, it is coming from the pulse processor. It comes on the going to the computer, getting analyzed here. And in the computer, they are giving in the real time. They are always going to give you the input what the things are going on. And believe me, the softwares are very much developed nowadays, and that they will just analyze everything for you. But as a user, we just always know that exactly what is going on the software, so that as you know that the software is the software is like that. It will give you, sometime it can also going to give you the garbage in and garbage out. So as a user, we should know that what are the software tells us about, right? So when you go for the chemical analysis of the ACM, so the question is that what is the qualitative analysis you are going for that? What are the element you are going for this part? So which element it can gives you, so that we can tell that what are the elements we are getting from this part? What are the elements coming? That element A, element B, element C we are getting for that. So our aim is to that get as many X-ray count as possible from the system. But while doing that part, just beware of the specimen damage. So when the electron beam comes, as I told you in the beginning of the talk, sometimes it may happen that the beam will damage this particular part, and there's some carbon contamination may can come on that. So as a user, we are a bit careful on this part. And then also you need to know the peak identification. We need to know for different energy level, what are the K family, L family, M family, like that. They are coming on this part. And this is the overall ACM skin, how we'll be looking on that. So we are getting the EDS peak, the X-ray peaks coming, that X-ray spectroscopy peak on this part. And the softwares are, or they themselves, they are so developed that themselves will fit with the peaks there. Not only they will fit with that, they also give a quantitative information how much of the element present in the system from there. So this is overall how the X-ray will look like that. So now if you can take from any of the periodic table that normally comes with any of the that EDS companies are giving on that. So you can see that this is the energy level. So this 16, let for example niobium, 16.616, this is the K alpha energy, and 2.16 the L alpha energy. So K alpha energy means when from the L cell to K cell, one electron jumps up, this much energy is coming out. So these energies are distinct from every element in the periodic table, and the software, they can tell you, so they can just measure this energy, and if the software or the instrument is properly calibrated, just by measuring this energy, they can tell you that this is coming from the niobium or the iron or the any other element in the system. They're going from that. So now go for the quantitative analysis. Quantitative analysis means what it can give is that it can give you the energy under the curve. So when you are having X-ray peak, it can first measure what is the energy, what is the area of this entire park. It can also measure what is the background, and then subtract the background from the main peak or main signal, and then give you the what is the area under the graph it is coming, and based on that it is going for the what amount of the element is present into the system. It can give it to you. So again, I'm saying that the modern day microscopes are very much developed, so the software himself will do the entire work for you. But we just need to know that what work is going on in the background, so that if there is two very close peaks, then sometimes this background preparation needs some help from the user part or some user input required from that part. So when you go for a limitation, there are some total limitation also is coming there. So that imaging resolution is a 0.12 nanometer, but as you know that in a volume, the material introduction, the AC image is coming in the top of the PRSF volume, but the X-ray information is coming in the slightly bottom part. So that means there the beam is bit higher. So even though the image resolution is 0.12 nanometer in ACM, but the specimen is X-ray resolution is coming on 30 nanometer. It is not that much fine from there. Sensitivity something around 0.5 to 1%. Below that you cannot get it. If it is above, definitely you can go for the EDS. But below, if your element is present below 0.58%, you cannot go from that part. Quantification is 5 to 15%. Roughly the accuracy can give it to you. And for EDS, it's one more important information is that the quantification is possible only for the elements for higher than the Z equal to 11, for higher Z number. It is not that X-ray is not generated for the low atomic number element or for the hydrogen, carbon, oxygen, like that. They are getting generated, but during traversing the part, most of the time they are getting absorbed in the detector itself, but they may not even come out from the material from there. Third thing is that the mapping of the part. Mapping means where they have been there. So this is one more strong point of the ACM or any of the electron microscopes. So they not only will tell you the image, they not only will tell you the chemical information, but they can also tell you how they are getting distributed here. So in this AC image, when you do from the different chemical analysis, we can say that. So in this AC image, we are having a Fe, we are having O, and we are having the other element, let's say aluminium. So we can get that how this element they're getting distributed here. So in the same image. So you not only get the microstructure part, but in the microstructure part, you can also get the microchemical part or how the element they're getting distributed into the system. This is another one example. So here we are getting from the iron. In the iron, we are getting again the oxygen, and the this is from the yttrium part. So yttrium, iron, and oxygen. So this is on the nuclear materials for working on that ODS still for nuclear reactor application. So yes, probably from here, I'm just going to finish today. This is one of my very favorite slides when you're talking about any other imaging part. So this is from the very famous book by the Williams and the Carter. So here you can see that one rhinoceros, right? Basically there are two rhinoceros, but they are coming one back of the other. So now as we know that, as we know the animal, we are familiar with an animal, so we can see two rhinoceros. But if you do not know anything about that, we can think about this is the basically two-headed beast with the four legs, right? So why I'm trying to say is that electron microscope is a technique in which you are always getting a perspective view. We are getting a 2D image of a 3D object. So most of the time the 3D object come on a 2D image. So you should know some sort of the idea of the materials, how it looks like that, so that you can correlate your understanding much better way. Thank you. Thanks for your kind attention.
My sincere thanks to Dr. Chanchal Koch sir for the valuable presentation on the microscopy and characterization techniques. Since we all are working in a material related concepts, this is the backbone of our research work. Now the session is open to the participants to clarify their doubts. Please clarify your doubts.
I mean, if you are having anything, I mean, right now you can ask me, or I already shared my email ID. I mean, that also you can anytime you can share with me.
Yes, sir.
Anything in the chat box? I think few questions are there. Okay, so the feedback session.
Participants are requested to clarify your doubts. So once again, my sincere thanks to Dr. Chanchal Koch sir for the valuable presentation. We can
Thank
wind
you,
up the session, sir.
Thank you, sir. Thank you.
Thank you, sir. Thank you very much.
Good night. Sir.
Thank you.
Sir, hello.
Yes,
Yeah.
yes.
Sir, I have one question, sir.
Yeah, please.
Yes. Session was very wonderful, sir. I want to ask one question regarding. I have tested one material. I want to just verify whether it is sustainable or not. I have mixed as a base material. I have used PLA, and in that PLA I have mixed papaya powder, moringa powder, and graphene.
Okay.
So, is it sustainable material, or whether I have to check by using which method, if I want to claim that particular material as a sustainable material, so which type of test it is
Now,
required?
which way you want to go for that? Which property you want to test for that? You want to know the
Mechanical
structure?
properties. Mechanical properties. I want to check.
Mechanical properties. Then I do not know that which form the materials is there. So it is a powder form, right?
Yeah.
Polish powder form. So maybe you can make a
No,
pellet.
no. I have made filament, sir.
Oh, okay. In the mechanical property means, let's say you are interested on the
Hello.
strength of the material.
I have made filament by using
Okay.
this mixing these three material.
Yeah. Okay. So in that case, on the mechanical behavior means there are
So I
different
want
parts
to
will be there.
know which type of method should I go for checking its sustainability.
Yes, so what we can go for that. So let's say first you want to know for that whether the material is a. I understand that it will come out from a ceramics part, right? It's become a ceramic material. So when you go for that part, as you are using a different powders from that.
You
The
are not
graphene.
audible, sir.
I'm not audible. Hello.
Yes, sir. You are
I'm
audible.
audible.
Sir, can you tell for which application you have made that filament?
Am I audible? Then I can answer. I can hear you. I can hear you.
Yes, sir. You are audible.
Hello, sir.
Audible there? Yeah, I am. I mean, you are
You
audible
are
to
not
me.
audible, sir. Sorry to disturb you.
Am I not audible now?
Yes, sir. You are audible. I can hear your voice.
Okay. Maybe I just take out my video. Maybe the bandwidth problem. I just take out my video. Okay. Maybe it will be a bit better. So, sir, what is there is that if you want to go for the mechanical behavior of the part, so first you know what is the structure of the material it is going on that. Okay. So for that you can go for that. You can just go for the visual inspection, and also if you can go for, let's say, the optical, how it will work for that. So as you are giving a graphene, so and understand graphene and then different powders are going from that part. So basic optical microscope you can go for that, how the normal structure going from this part, and then if it is required, then also you can go for the graphene structure or how the microfiber they're going from that. You can plan for an ACM. That will give you the structural part. Second thing you can go for is mechanical property. So you can look the surface. So how the surface will look like that. So if it is a ductile or the brittle part, so how hard it will be. So in a ductile or the brittle, by looking the surface, if they are having very high faceted part, then you can think that this is the basically brittle surface, or it is a hard material, but with the brittleness will be there. And ductile means it will be having, let's say, try to break the system or break the part or break the filament there. And after breaking, you can find the surface is much more smoother part, and the grains are much more smoother. Then you can think is about this is a ductile material, or hardness is relatively low from that. Okay, so this is how you can just confirm its sustainability of this material.
Okay, sir. Thank you very much, sir.
Okay.
Thank you, sir.
Okay.
Any other clarifications from participant side? Okay. My sincere thanks to Dr. Chanchal. Thank you, sir, for your
Thank you, sir.
valuable presentation, for sharing
Thank you,
your knowledges. Thank you, sir.
Thank you, sir.
Thank
I'm
you,
logging off, sir.
Yes. Yes, sir. No more clarifications raised by participants. So we can wind up the session 6. Thank you all. Kindly give the feedback within 20 minutes. Thank you.